Gerrit works for Datamine, where he heads the geology team in Africa. His tasks vary from geological modeling and due diligence studies to support training and software implementations. He has experience in exploration and production, but is focused on resource estimation for the last plus 5 years in various geological environments, from tabular iron ore and manganese to gold, chrome, copper, mineral sands, PGEs, and coal. Gerrit has an excellent knowledge of various linear and non-linear estimation techniques. He applies these techniques in consulting projects, but also presents specialized resource estimation courses to clients. Thank you very much, Gerrit. You can carry on.
Thank you, Nicole. Thank you, and good morning, everybody. Thanks for inviting me to have a talk, and I've certainly enjoyed all the talks yesterday, and we're looking forward to this afternoon's talks. So I'm going to talk about optimizing estimation parameters, with the focus being on the resource estimation, the chat. So I hope I'm not boring the more experienced practitioners. I think a lot of things have been spoken about these topics, and it might be something old for a lot of people, but maybe there's somebody in the audience that can learn something today, and maybe it's just an interesting topic to revise. Right, so let's look at the agenda. I'm just going to give you a brief overview of a typical resource estimation workflow. Then we'll talk about a little bit of background into ordinary kriging and the volume variance effect, just so that we set the scene for how we are going to optimize our estimation parameters. Then we're going to look at selecting our estimation parameters, the various aspects relating to that, and then we're going to just work through a practical example in Supervisor to just show you how it's practically done. Most of my information was from Jackie Coombs' book, the Art and Science of Resource Estimation. So it's a very nice book. If you guys haven't read it before, it skips all the mathematical equations and simplifies resource estimation into a very user-friendly format. So probably it's a very good introduction. And if you want more detail, then you can go and look at all the GeoStats papers and books out there. But a very good introductory book to resource estimation. Okay, so I think a couple of speakers yesterday also gave this definition, but if we just set the scene on what is a mineral resource, so it's a concentration or occurrence of a solid material or of economic interest, right? So obviously, I think some of us have been exposed to lithium recently. I've been exposed to the lithium brine project, so that solid might have to be revised there. And then also the location, quantity, grade, continuity, and other characteristics are known or estimated or interpreted. Okay, so we're going to typically estimate known values from our drill holes or samples into unknown areas, and there's various methods that we use for that, and we're just going to look at some ways on how we can optimize some of those parameters that we use during that estimation process. If we look at a typical resource estimation process, and this is just a short summary, based on my experience, there might be various other factors not listed here, but this is a quick summary, and it's also not a process that you follow step by step, but you might go forwards and backwards in some of these steps. Okay, so typically we'll have our data gathering phase, our drilling and sampling phase, where we get our samples or our information at known locations. We have a database validation phase where we make sure that our data is correct and accurate and good enough to be used in our resource estimate. Then we will do our geological interpretation, which is very, very important, and probably, as I think Marius mentioned yesterday, the most important factor in resource estimation, which can also lead to the most errors if we do that incorrectly. Then to standardize things, we code and we composite our data. We group our data into similar groups, into populations that behave similarly. We do some stats and domains to make sure that our grouping and coding was correct. Then we do our variography and we see, how does our grades and characteristics change with distance and with direction. And then after that, we're going to look at our parameter optimization and defining our parameters that we're going to use during our estimation. And that is where I'm going to talk about today. Once we've got our parameters, we can go and estimate our grades into our unknown areas. After that, we go and validate it and make sure that our estimation is good and we're happy with it. And then we can move on to classification and reporting and all the tasks that involve that. So that's a very simplified summary of the resource estimation process. And as I said, I'm going to focus then more on the parameter optimization phase in that green box down there. Okay, so for us to do that, I'm going to give us just a brief introduction to kriging. And it's difficult to keep it too brief because then you skip a lot of things. So I'll keep it as short as possible, but it will just set the scene and explain a couple of things. If you want to know all the mathematical equations, then I think I would rather advise you to go and look at some of the many geostatistic books out there. But this is just a sort of a very brief overview. So I think most of us as geologists know the story of Dani Krieger. He was some say a surveyor, some say a mining engineer. And he saw that with empirical comparisons between estimated and actual grades, there was a difference. So he got his estimated samples from developments in the gold mines, and then when they did the actual face sampling, he saw there was a difference from what he was expecting. So they discovered a consistent pattern. The estimated high grades were always lower than the predicted grades, and the estimated low grades were always higher than the predicted low grades. And that was termed the regression effect. So for example, if they estimated a panel to have a grade of 8.9 grams a ton, then it will produce 7.2 grams a ton. Or if the panel was estimated to have 1.7 grams a ton, it produced 2.7 grams a ton. So there was this consistent pattern that they saw. So they said, how can we account for this and why does this happen? Okay, so the main reason for this happening is what they termed the volume variance effect or the regression effect. And it basically, as I think Marius demonstrated with the bucket and the teaspoon example yesterday, it's basically the grade dilution as we select larger volumes and become less selective. Okay, so there's a nice image in Matherian's book, 1961, where it basically says if we sample development C to D and development A to B, they're at the top, and that was all high grade, and we decide to mine that trapezium panel, then we're not just going to get high grade, because the boundary between the rich ore and the poor ore is likely to have that dotted line signature like we see there. So we are going to get some low grade ore in our panel, and we are going to also exclude some high grade ore because of that boundary. So that's basically what it boils down to. If we look at it in another way, if we look at two blocks, on the left hand side is a block that's colored red with a grade of 8, and on the right there's a block with a grade of 11. So if we had a cutoff, let's say, of 10 grams a ton, obviously the block on the left would be waste and the block on the right would go to our plant. So that might be a resource block, it might be a large panel, it might be, but let's for this example, let's assume that is a resource block that we estimated from our resource model with our exploration drill holes that's quite far apart. However, when we go and do mining and we mine on a smaller scale, a more selective scale, we will see that that block that had a grade of 8 actually consisted of various smaller blocks, some of them with actually very high grades, as you can see there, those green blocks. That's much higher than the cutoff. So we can see where we thought we just had waste, we have in fact ore, some of it very high grade, and on the block on the right, where we thought we just had ore, we can see we have almost 50% waste, which is made up of those lower grade blocks. So that is what happens in the volume variance effect. We can also see that in our grade tonnage curves. That's an example where we've got a block model with a 5 by 5 meter dimension. This is a block of 20 by 20 meters. The 20 by 20 meters is the grade tonnage curve. And what we can see is that we generally have differences: lower tons above our mean and higher tons below our mean, and also lower grades with the bigger blocks when we are above our mean, and when we're below our mean, we get actually higher grades in the big blocks. So that is exactly what we see in practice. Okay, so this is obviously very crucial if you're a grade control geologist and you don't understand why you're not reconciling well to your resource model and so on. This is basically the first reason why they developed kriging. So Dani Krieger then worked with the geostatistician or mathematician George Mathurin on creating a technique that would accurately reflect selectivity in mining. Okay, so they wanted to create a linear technique that would have the least overall difference between the predicted and the actual mine grades, and it needed to be unbiased. So when we look at linear estimation for some of the junior people present, linear estimation simply refers to the weights that are applied directly to the sample grades without any transformations. And some people also explain it as the weights that decrease with increasing distance linearly. Okay, so it's a linear estimation. It's quite a simple mathematical estimation. And then the actual grade. So obviously you can see there in the definition they say the difference between the predicted and the actual mine grades. Okay, so we'll talk about that a little bit later, about how do we get the actual grade if we haven't mined it yet. But the samples and the variogram has information on the original pairs that we used during the variogram modeling, and we're going to see later that you can actually determine the actual grade before being there based on your data or your variability. So the kriging system generates weights that ensure an unbiased linear estimate that has the least overall variability between the predicted and the actual grades. These weights are a function of the variogram model and then the distance between other samples and the blocks being estimated. Okay, so as you can see, the variogram has a importance, and the variogram model should accurately reflect the variability that we observe in our data. Okay, we'll look at this in more detail in a practical example now. So basically, what they say there this is basically straight from Jackie Combs' book. She presented it in this quite simple manner. The two conditions that they wanted to meet was the least overall difference between the predicted and your actual grades, and it needed to be unbiased. So we can write that as the predicted minus the actual grade squared is minimized, and then the sum of the weights must be 1. That can be rewritten as the sum of the weights times the grade to give us a predicted grade, minus the actual grade squared is minimized, and secondly, the sum of the weight is equal to 1. And if we combine those two equations, we get the combined equation there at the bottom, the sum of the weights times the grade minus the actual grade squared minus that Lagrange multiplier times the sum of the weights minus 1. Okay, so we can see there the Lagrange multiplier crept into the equation, and that basically for now, without going into too much mathematical detail, measures the degree of bias that exists. What we notice is if we have clustered, sparse, or data that is extrapolated significantly, this will result in a higher Lagrange multiplier. Okay, so that's basically the Kriging equation, and we're going to look at an example now of how it's applied. Good. So let's just go back once. Okay, so let's assume that's our little block, one of our blocks in our block model that we want to estimate. The blue balls in there is the discretization points. I just added 2 on 2 by 2 on the one side. So obviously that's in all the directions, and we typically use more than those. And then surrounding the block is some of the samples that we're going to use, some of our drill composites. So the first step is to determine which samples we're going to use to estimate, and we use a search volume or a search ellipsoid, or it can even be a rectangle around our block, and we center that on the block, and it selects the samples that we want to use to estimate. We can obviously divide those that ellipsoid into octants and sectors and make it more selective, but that can also introduce all sorts of unnatural artifacts. We can also expand that search volume, which also might introduce some unnatural artifacts. So let's keep it simple for now, but that's basically the first step. We select the samples and the orientation of the search ellipsoid. Then we measure the distance between each of our samples and all of the discretization points in our block. Then we use those distance, and we take our variogram that we modeled so nicely, and we read off the variogram values. Then we average those variogram values to get a sample to block variogram value, and we repeat that for all of our samples. Then we go and look at the effect of the samples between themselves, and we measure the distance between each sample and every other sample. And we also get a variogram value for every sample pair. What we then do is we take all of that information, we put it into our Kriging system, and that will essentially calculate the weights for us, the Kriging weights. So we can see it depends on the sample spacing as well as the sample to block spacing. The weights are applied to the respective sample grades, and we generate the ordinary Kriged estimate. Okay, so very simple steps. If we look at it, basically the system tries to solve these matrices, and what we see on the left, matrix A, is basically all the covariance values between the sample pairs, and then on the right hand side on matrix B, we've got the sample to estimation point correlation, and in the middle then the system solves for the weights for each sample. Okay, good. Okay, so that's a very simple explanation of what happens in the Kriging process. So we can't speak about Kriging without just mentioning Kriging variance, and I'm going to show you why we talk about Kriging variance, because Kriging variance is used later as well when we want to calculate that known grade, which we don't know. So the Kriging variance is calculated from the Kriging system, and it's basically the sum of the sample to block distance variogram values times the Kriging weight minus the average of the variogram value between each and every discretization point in the block size plus the Lagrange multiplier. Right, so to summarize, as I said, it's the sum of the sample to block variability weighted by the Kriging weights minus the variability in the block plus the Lagrange multiplier. Okay, so you can see there's no mention of grades in there. They say there it's based on the sample configuration surrounding the block and the variogram. Sample values are not incorporated into the Kriging variance at all, as you can see. So if we look at those examples there at the bottom, we can see that block is surrounded by 6 samples. On the left, we have sort of grades that are less variable. We can see 5.5, 6.5, 5.2, 6.1, 6.2. So all of them are more or less the same. Versus on the right, we've got the same sample spacing, the same block size, but we have a lot bigger variability in our grades. So you can see 12.5 versus 1.5, 19.2 versus 1.2. So the variability on the right is much bigger than the variability on the left. Therefore, the risk in the grade on the right is much bigger than the risk for the block on the left. So we shouldn't confuse Kriging variance with telling us that it's necessarily the risk in the estimate of a block. It's rather more a function of the sample spacing and then obviously also the block size. Okay, so just to keep that in mind. So Kriging variance is good to show sample spacing, but not really the variability in the grade. We'll typically see that more in our variogram model. If we just quickly break down this Kriging variance equation further, so there's the 2 parts of it. So the first part, which is the variogram values of the sample to the blocks times the Kriging weights. Basically, how that's calculated is we collect the distance between the samples and the discretization points. We use the distances and read off the variogram values, and we get an average to get the sample to block variability. For the block variance, we collect the distances between the discretization point. We take all of those distances, we average them, and we read out a variogram value for the variability inside the block. Okay, so we can see there, if our block is all the same size, if we've got parent cell sizes, which is consistent across our deposit, or then all of these values will be the same for the same block size. All right, so that's a brief introduction into the Kriging system. If we look at the different estimation parameters, we've got obviously domaining. So if we look at the definition of domaining, that's the volume where the geology is more or less homogeneous and it contains a single grade population. And this is very, very important if we want a successful estimate. So this is the way that our data is grouped. We must also consider things like our boundaries, is it hard boundaries or soft boundaries, gradational boundaries, and how are those domains split. Another estimation parameter is the block size. So in other words, how big are those blocks that fill up our volumes? If we get too small blocks, it will produce a false sense of selectivity. And we might get there and we might realize this is not exactly what we thought it might be. So it will cause a too smooth estimate. A lot of people use a rule of thumb, which is between a half. Some authors say half of your drill hole spacing, some say a quarter, some say 1/10 of your variogram range. So there's various rule of thumbs out there, and it's difficult to quantify. So probably the most important thing is your ore body, to specify a block that fits into your ore body, and then also eventual mining selectivity. So for instance, if you're going to mine at 10 meter benches, then it's good to have blocks that's 10 meters high, maybe, for example. Then another estimation parameter is the discretization points. So those are the points that we add inside our blocks, and those will help us to account for the volume variance effect, and we then add those sphere points. Most people will use 3 by 3 by 3. I think that's maybe because it's a reasonable value. It's a default in a lot of the software packages. But it would be nice to quantify that and see why we use 3 by 3 by 3 or 2 by 2 by 2 or whatever you use. The thing with discretization points is it's good to have many. We want to have as many as we can, but it will make our estimation process slower. So the more we have, the slower our estimation process. Then the search ellipsoid. So that's now the area or the volume in which we select our samples to estimate into our block. Those are typically determined by our variogram ranges. So depending on if you've got an anisotropic or isotropic variogram, you might have different distances and different directions. And basically you will get a little rugby ball or a soccer ball, or even as I mentioned, a rectangle, and that will select the samples that will be used for your estimate. But we also generally have to consider our geology. You have to think about your sample spacing, your orientation of your ore body, your size of your ore body, things like that. Practical things need to be considered as well. Then another parameter is the minimum and maximum number of samples that we use during our estimation. So what is the minimum number of samples that we use to get an estimate, and what is the maximum number of samples to get for an estimate? Okay. A lot of people try and reduce the maximum samples. I've done it lots of times because I think I'm going to get a better estimate, and that is not necessarily the case. And in fact, you can introduce some bias if you use too little or too few samples. They say there for highly selective zones, limit the maximum number of samples, but again, it's a subjective number, and it will depend a lot of times on the experience or the person that does the resource estimate. Then we can also look at the number of samples per drill hole, and a lot of the software packages allow you to limit the samples per drill hole so that all your samples doesn't come from one drill hole, but your data is spread out across the search ellipsoid. I didn't mention sectors and octants here, so that's something else. But these are the basic estimation parameters we're going to talk about. The question is, how can we optimize these and reduce subjectivity? Okay, so I want to reiterate that your geological knowledge and common sense needs to prevail over these methods, but these methods you can use as a tool to guide you in your decisions. So Dani Krieger proposed a goodness of fit statistic to evaluate the appropriate estimation parameters back in 1996. Okay, and the two statistics that he developed was the Kriging efficiency and basically the slope of regression. The first one, the Kriging efficiency, basically measures, if we look on that image there, that histogram on the left-hand side at the bottom, we can see the blue histogram is our estimated distribution from our block model. And then the actual distribution is the shaded gray polygon. So we can see they differ slightly. So basically, Kriging efficiency measure the percentage overlap expected between your estimated histogram and the histogram of a true block grades. If we get a Kriging efficiency of 100%, it's a perfect match. As our data becomes more sparse, if it's extrapolated more instead of interpolated, or it's clustered, our Kriging efficiency will drop, and it might even be negative. So a lot of the times we get those things as negative. So that's the first goodness of fit measure. The second one is the slope of regression, which is demonstrated there on the right. We've got there on the y-axis our kriged estimate, on the x-axis our samples. That's actually just a cross-validation, but that will be the kriged estimate versus your actual values. And then the slope of regression is drawn between the estimated and the true block grades. Okay, so the true block grade will obviously, if it's a perfect estimate, it will be a 45-degree diagonal line, but we can see in practice it typically is not, and that it will deviate slightly from that, or hopefully slightly, but it will deviate from that 45-degree line. So we want to get it as close as possible to 1. And if it's close to 1, it means the estimated high grades and the estimated low grades correspond to the true high grades and the true low grades in our data. Okay, so we're going to look at how these two methods are used to optimize our estimation parameters. There's a little bit more theory that I added just for some background. So we kept on mentioning, true grade and actual grades in our definitions. So what if we don't have true historical mining data? Okay, so this explanation I found in Isabel Clarke's paper of 2015, and it's probably the easiest for me to understand. So Dani Krieger had lots of actual data. So that was the actual data was his phase samples that he compared to his estimate. So the estimate samples he got from the development drives. So he had lots of actual data to compare it with. So he took his development samples, estimated the panel, took all the phase samples, and then compared it to. We obviously don't have that luxury. So what I think Mathieren showed was that the variogram model was mathematically equivalent to calculating the covariance model. The covariance between two samples a certain distance apart can be found from our total SIL on our variogram minus the variogram value at that distance. The dispersion variance can also be calculated as the total SIL on our variogram model minus the average variogram within our block. That is now each block inside our block model. So the covariance between any two sets of entities, our samples or our blocks, can be derived from the variogram of the samples. All right. So we can see a lot of the things hinge on our variograms. So a lot of people ask, does the variogram really matter if I don't model it correctly? Or but we must do our best to do it as proper as we can, because we can see a lot of things are dependent on our variograms. So if we look at it mathematically, I think a lot of us know these equations. They're very simple, and they're also used frequently by all of us. But our block variance is our total SIL of our variogram minus the average variogram within our block. We'll get to see how we get that now. The Kriging variance, we looked at that earlier, but that's just in a different format. We see that's the weight, the sum of the weights plus the variogram values between the samples and the blocks, plus the Lagrange multiplier minus the variogram values within the block. Okay, so the block variance, or not the block, the dispersion variance. So that's the Kriging variance. And what we want to end up is we want to end up with our slope of regression and our Kriging efficiency, right? So for each block, our slope of regression can be calculated as the block variance minus the Kriging variance plus the Lagrange multiplier divided by the block variance minus the Kriging variance plus 2 times the Lagrange multiplier. The kriging efficiency, on the other hand, can be calculated by the block variance minus the kriging variance divided by the block variance. And the block variance is simply calculated as the SIL minus the F value. And this F value, which is basically the average variogram within each block, is typically calculated by your estimation software. So it's not necessary that you have to go and calculate the distance between all the discretization points and average them out and get that value. So so that is, as I said, calculated by your software typically during your estimation run, and that will be the same. If the block is the same size, the F value will be the same size. Okay, good. So that is basically how we can get those known grades and compare them to the estimates. I'm going to quickly walk you through a estimation or a optimization example in Supervisor. I think I see a lot of people in the call know Supervisor, so I'm sorry if that's boring to you guys, but maybe some of the other people don't know about it. But it's fairly simple, the simplest software in which to demonstrate how we would optimize our estimation parameters in practice. I hope everybody can still see my screen. I think so, yeah. Okay, so this is our data, and this is in Supervisor. This is a gold deposit. You can see it has a north-south strike, and the ore body dips 60 degrees towards the west. So before we do any sort of geostatistical interpretation, our geological knowledge is of utmost importance, and definitely the thing that should guide you all along when you make decisions. So we're going to quickly do variography and then optimize the estimation parameters and also the drill hole spacing with this software. So I think you might use different software packages, but the theory behind it remains the same. We've got about 8,500 samples. They are composited down the hole in 1 meter composite lengths, and the drill hole spacing is about 10 meters. Okay, so first thing that we're going to do, so we've composited it and we capped our data. We capped it at 100. This data set is, if we just quickly look at the histogram, it is positively skewed, as we would expect from a gold deposit. If we put it on a log scale, we can see not the greatest distribution. These are probably limits of detection on the left-hand side, but we can see there is some peaks. But let's just use the data as it is. Okay, so we've composited and capped our data. Now we're ready to do our variography. So the first thing we're going to do, we are just going to investigate the variability or the variograms in a horizontal plane. So I'm going to put it in a normal scores transformation just because it's so positively skewed. And I'm going to create 18 variograms 10 degrees apart. So let's just quickly run that. So there is my variograms at every 10 degrees, and then of course my contours. I can zoom in there. I can see there's a definite trend in my variograms. I can play around with the lag, and I'm going to put it on 10 because that's my drill hole spacing more or less. And you can see this is where things become subjective. You know, if you just look at the contours, you might put them depending on who you are or what time you woke up, you might put them on a different place. But I know my strike is north-south, so I'm going to go for the north-south direction. I can look into the variograms. I can see, yep, that's about 80 meters. And I can go through the different directions and see if there's something further. But I know this data, so I'm going to stick to that direction. We can view it in the 3D viewer and we can see, yep, it aligns to our data. So I'm going to go with that. So we looked on that horizontal plane. The next thing we are now going to do is we're going to just look on a cross strike vertical plane. So we're going to add that plane. And this is now looking on the green plane, sort of in this direction. So we're going to look at that. We can again zoom in a bit. We see there's a trend there. Very nice. I know my dip is 60 degrees. So instead of putting it at 50 degrees, which some people might do, or 70 degrees, I'm going to go with my geological knowledge and I'm going to go for the 60 degrees. There, it's about, let's see here. It's about 50 meters, a range of 50 meters in that direction. We can again confirm it. We see there it lines perfectly to our dip, expected dip. And we can do a third plane, which will cut through our strike in our dip direction. If we just view the plane, it's now the purple blue plane. So we're now going to look in that plane and determine the variability in there. I don't see anything in terms of a plunge really, so I'm going to just align it there for simplicity now. We can see it will align into our strike again. And then we can, what we basically did is we determined the directions of continuity. We can then go and create our variogram models. So we can see there's my downhole variogram. Good, the auto-fitting did a good job with this data. And then my 3 directional variograms are also fairly good auto-fitted. Okay, so we can look at them. I'm happy with the way that the auto-fitting was. Just to save time, we can look at our search ellipsoid and we see, yep, it makes sense. It's what we expected. And we are now ready to do our estimation parameter optimization using the kriging efficiency and the slope of regression. So we're going to add our kriging neighborhood analysis. That's where we optimize our estimation parameters. So basically what it does is it varies different estimation parameters and it calculates the kriging efficiency and the slope of regression for each scenario. And then it plots these on a graph and we choose the scenario which gives us the best kriging efficiency and the best slope of regression. So let's run that. The first guy that we're going to do is our block sizes. So I'm just going to go with a 5 by 5 by 5, 10 by 10 by, let's say 5, 25 by 25 by 5. Let's go 50 by 50 by 5, 100 by 100 by 5 maybe, and 200 by 200 by 5. So those are the block sizes that we want to investigate. Should our block model be that size or this size or bigger? Okay. As mentioned, use common sense as well. We know our ore body well now. We know the thickness of the ore body and things like that. So based on my ore body knowledge, I wouldn't expect to go for the 200 or 100 even, but let's just demonstrate the shape of the graphs. Under parameters, we can set the various search parameters, the minimum and maximum samples and so on. I'm just going to leave it as it is. It will use the variogram ranges by default, but you can change that. So let's run that quickly. Great. So there's our graph. We can see, luckily, this also confirms our suspicion that the bigger blocks are out of the question. We can see. I like to switch off this the whiskers. We can see that our best kriging efficiency was generally achieved by the 10 by 10 blocks. We can even go for the 25 by 25, although the slope of regression drops off there. We can see these slopes of regressions are more or less the same. Still almost above the 0.9 we want, and the kriging efficiency is slightly below the 80%. Okay, but so I'm going to, just for this exercise, I'm going to go with the 10 by 10 meter block, and then I'm going to just click and add the samples. So the next step that we want to investigate is the number of samples to use in our 10 by 10 meter block. We're going to just limit this to 50. Let's make it a minimum of 2 and a step size of 2. Let's update that quickly. I'm just quickly running through. I think I'm running out of time. Great. So there we see this sort of same thing with our kriging efficiency on the left and our slope of regression on the right. We can see it increases with increasing number of samples, and then it sort of flattens out. So we want to choose the maximum where we see a flattening in our kriging efficiency and slope of regression. So it doesn't matter if we use more samples. It's not going to really improve our kriging efficiency. And we also don't want to, although these kriging efficiencies and slope of regressions are low, we don't want to end up with too many blocks that isn't estimated because of a lack of samples. Okay, so we would rather just give those blocks a lower resource category, maybe, and than not having them estimated. So we can also look at the negative weights. So in this example, there was no negative weights produced, but typically you will start to see negative weights if you have too many samples. And that's just because of the screening where the samples are after each other, behind each other. But that's we're not going to talk about that now. So I'm gonna say give me at least let's say we want at least 4 samples to be practical, and on the maximum I'm going to go with a big value of about let's say 30. After 30 there's no big increase, maybe even 25, maybe there 24 samples. So there's a very little increase. So as I said, try big values. Remember that your samples will be weighted. So even if they are far away from your block being estimated, they will have such a small weight that they shouldn't really have an influence on it. But at least you won't be biased to your samples that's close to your block. Okay, so we've got that sorted. The next thing that we want to look at is the search volume. So it will give us some default ranges. These are ranges from our variograms. So we're going to quickly just run this. In this example, we can see all of them are more or less the same. So I'm going to just go with the ranges of my variogram. Then we're going to look at the number of discretization points. So for this guy, we are going to do something like 1 by 1 by 1, 2 by 2 by 2, 3 by 3 by 3, 4 by 4 by 4, and 5 by 5 by 5. Okay, so what we want to see here, as I mentioned, the more discretization points you have, the slower your estimate will run. Okay, so we want to get the maximum, but not too many. Otherwise, we're going to unnecessarily make things slower. So we can see 1 by 1 is out of the question. The one obviously after 3 by 3, it flattens out. There's the box and whisker plots of our, but we can see there's a slight reduction. So I will typically go for, in this example, let's just use 2 by 2 by 2. It gives us a good kriging efficiency and a good slope of regression. Not much better than, or not much poorer than 3 by 3 or 4 by 4 would. So that's our estimation optimization. So we would go with a 10 by 10 meter blocks, 4 to 26 samples, and then the 2 by 2 by 2 discretization points. Thanks. Nicole, am I over my time?
No, you still have a few minutes, Gerrit.
Okay. Let me just see if I've got I just have a final slide. Right, if we have a few more minutes, what we can also optimize is our drill hole spacing. So what we can do is we can basically use different drill hole spacings, and we can see how that will influence the kriging efficiency, and then choose the one with the best kriging efficiency. So let's quickly do that exercise. So we're going to go to the grade control drill hole spacing analysis. Okay, so let's look at a couple of options here. So let's say we wanted to look at a 2 by 2 meter drill hole spacing with a 1 meter downhole sample. We want to look at a 5 by 5 meter. Let's look at 10 by 10 by 1, 20 by 20 by 1, maybe 50 by 50 by 1. And yeah, let's do 100 by 100 by 1. Okay, so we're going to investigate, what the effect is of those different drilling grids. And what's nice about this tool, specifically in this supervisor, is that you can specify a cost associated with different patterns. So obviously, the more drill holes we drill and the more samples we have, the more expensive it's going to be. And we can sort of weigh, is it going to be worth, is it worth it to spend that much more money, but only have a little bit of increase in our kriging efficiency? So that's the idea behind this tool. So let's quickly run that. Maybe I was optimistic with the 1 by 1, the 1 meter sample interval, sorry. There we go, it's almost finished. Okay, so if we look at the kriging efficiency first off, I'm going to just minimize my whiskers again just to... Okay, so the reason why it's a box and whisker plot is because it does it on an area. So it's not just for one block. You can choose to do it only on one block, but it does it on a 300 by 200 meter by 40 meter block. And the same with the other ones. It does it on the whole extent of our data. So it's not just a one point that you might see. This is for a range of blocks. So we can see these are block sizes. Our kriging efficiency increases, then it decreases. So we can see we definitely don't want to go with a 100 by 100 meter block size. Our deposit is maybe too variable for that. We would likely to go, if we have got money, for the 5 by 5 meter drill hole spacing. That seems to be the optimum grid size or drill hole spacing. But we can also then, as I said, look at the cost. The negative weights, there's no negative weights, but the costs as well. So we can see there, way up there is probably the 2 by 2 meter drill hole spacing. It's very low. It's like 45 million, depending on what cost you put in there, but it's relative. So and then we can see down there at that 75 or 7.5 million, sorry. So it's a lot less than the 2 by 2. There, for the 10 by 10, we get this a cost that's almost a quarter of the 10 by 10, of the 5 by 5, which is the 10 by 10. So although the kriging efficiency only increases, slightly, our costs of exploration or drilling is reduced by a quarter, or is a quarter of what it was for the 5 by 5 meter. So and you can see how the cost drops for those, but then also our kriging efficiency drops. So maybe it would be better to go for this guy. Okay, so that's if I could just quickly just recap. So basically, if we summarize, Kriging provides us with a set of tools which we can use to optimize our estimation parameter and make it less subjective. As mentioned, always use your common sense and your geological knowledge and make sure your geological interpretation and domaining is correct. Be aware of the volume variance effect and account for that. Kriging variance provides a robust tool to show the data density. I didn't demonstrate it in maps, but it doesn't consider sample grades and it doesn't present true variance or risk associated with our estimate. Use our geological knowledge to guide our geostats and our estimation decisions, and basically use both as a tool and use them together to confirm your knowledge and your assumptions that you make. Consider nonlinear methods such as conditional simulation and uniform conditioning to investigate risk and your volume variance complications. Okay, so that's basically the end of my presentation. Thank you.
Mark has more than 25 years of experience in the mining industry. He has extensive exposure to the mining value chain, including early stage exploration, shaft sinking operations, mergers and acquisitions, and asset disposals. Mark joined AMC in 2018 as principal geologist. His primary responsibilities are undertaking and managing technical geological works, including mineral resource estimates, technical reporting, business development, and client support in relation to exploration and production advice. Prior to AMC, Mark was principal consultant and divisional manager for applied geosciences for Snowdon. And Mark, prior to that, worked for Harmony Gold as new business manager, where he was responsible for identifying project acquisitions for the company. Mark is currently the chair for the PERC Training and Education Subcommittee and a member of the Finance Subcommittee, and also a member of 3 of the United Nations Economic Commissions for Europe expert working groups who are developing the United Nations Resource Management System. So, Mark, you can go ahead. Thank you very much.
I thought I'd cut that down so it didn't sound like it was so self-adulatory. So anyway, everyone, I'm going to be doing something which is probably a little bit off the beaten track. So I hope it will be of interest. I actually found it quite interesting when I did the research. So I'm going to be talking about the concept of geopolitics and critical raw materials. Now, a lot of you will be seeing press statements and releases coming out with CRMs and SRMs on it. So they're not the stuff we as geologists normally deal with. So we're not looking at QA/QC. We're looking at the concept of how do countries and nation states control the economies through the consistent supply of the raw materials that they need to either drive the economies or to have food security and to have military security. So, for example, NATO has just convened a working group where NATO in itself is looking at being able to secure what they refer to as strategic metals and minerals. So they can then build missiles and build tanks because they can get the rhenium and the lithium and selenium and all the other nice fancy stuff that they need to build high-tech weaponry. So when we start talking about this concept of geopolitics, it goes back quite a ways, at least the early beginnings of the 20th century. A lot of it was related to naval power. So Britain rules the waves, American naval sea power, and why there was the arms race during the First World War, and everybody was building better and bigger battleships to control the sea lanes. So what we start seeing in this is, while we specifically define geographies in terms of the locations of countries and the number of peoples in countries, education levels of peoples in countries, we also, at least nowadays, but again, it goes back much earlier, that we're looking at natural resources. And by definition, natural resources means the metals and materials that we mine from the ground to support our economies. We tend to see them being defined in 4 different ways. Obviously, as I mentioned, natural and geographical, societal functions. So, growing populations, you have population growth, and that population needs to go somewhere. You're running out of natural resources. Are you having specific changes in your economy? So again, it ties into social, the 1930s with the economic collapses, around the world, but in America, for example, you had massive migration, so local geopolitical issues, so people moving from eastern states moving towards California. So you had John Steinbeck then writing The Grapes of Wrath. And of course, chronopolitical, so things that have happened in history. The one we're currently seeing, the conflict in Israel and Gaza, that goes back until post-World War II, when Britain, amongst others, created the home state of Israel and upset the local geopolitics of the region. We also saw that in the 90s with the Balkans conflict. Again, those fracture lines were covered up because of the Cold War, so you had relative stability. And then post-Cold War, a lot of issues in terms of historical religious issues starting to come and rise again. And it can get really complicated, so you start seeing these feedback loops occurring. And as you can see here, you can see how natural geographical issues then can tie into social geographical subspaces. So it's not a case of you just have one thing occurring, there's a knock-on effect. So very small actions or activities can have pretty much unexpected or unexplained consequences going through the system. Now you can see that we then start building up things which refer to as geostressors. So maybe you're not getting sufficient graphite. That is going to impact on your, your car manufacturing industry. As soon as that starts impacting your car manufacturing industry, you have to retrench people. You retrench people, then you end up with social unrest because you don't have sufficient money in the economy to then go and put them on some sort of benefit. That will then move on to something else. So you then may, for example, have issues in terms of food rights, a protest in the street, and so the whole thing can spiral out of control. And we get to something like the Arab Spring. That was more a political issue, but the concepts are very, very similar. But what we also need to understand is that when we're looking at geopolitics, we're not just looking at, well, we have the raw materials in the ground. So what you'll find, and again, with, say, for example, the American Inflation Reduction Act is to try and move the resourcing of raw materials onshore. So the concepts that you'll start hearing and reading about are things like onshoring, friendshoring, and nearshoring. So we're trying to limit the supply chain. So i.e. you don't want to bring in raw materials from another country. You want to try and source them either within your country or very close to your country of origin, preferably with states that you have friendly and stable relationships with. Where the critical gap is, and this is a document produced by the United States government looking at supply chains, it's all very well and good to be able to find or explore for, discover, and create a source of raw materials within country. But then the problem then comes in if you cannot process and refine these. And that's something we're going to be discussing later on. So while you may be able to find a massive rare earth project or deposit, the chances are you have to still take that material to China for processing. China controls 80% of the midstream processing for rare earths. So if you're trying to get rid of your dependency in China, it doesn't matter how good or brilliant your rare earth deposit is if you cannot process it. Salutary case would be Mountain Pass in America. Up until the 1980s, America was the world's leading producer of heavy rare earths. For various geopolitical reasons and also environmental reasons, they ceded that to China, and America is now highly dependent on the import of rare earths back into the country. For those that have been following it, when Mountain Pass was reopened, one of the things that occurred is a Chinese company then went and promptly bought up 20% of the share in the asset. And again, they were still having to move that material out of country. One of the questions that someone will raise is, well, why is it so difficult? Why don't we just go and build our own rare earth refinery in country? Well, it then starts getting into ESG aspects. One of the nastier side issues that come with processing of rare earths is a lot of them are carcinogenic, and there is environmental and social issues with producing and extracting rare earths. But probably the biggest one of all that we all know and talk about is the geopolitics behind oil. Now, this is one that will be familiar to most of you. This is from the Second Gulf War, so Gulf War II, where effectively America went in and, Gulf War I, where Saddam Hussein invaded Iraq. The Americans, or the coalition of the willing, went in and had the Gulf War, which was effectively over in 100 days. Why is this important? Well, have a look at this slide. Now, we can argue the metrics and we can argue some of the additional numbers here, but this is more to indicate that as much as people are protesting about leave oil in the ground and let's go green, if you look at the amount of money and revenue that oil generates, it is massive. The other thing which people tend not to really think about when they're looking at oil is if we stop oil production, you will have no or very limited clothing. A lot of our clothing is synthetic. Look at your laptop. It's got a lot of plastic in it, your car, just the roads we drive on. It's all byproducts of the hydrocarbon industry. But if we go and add up all the other metals that we currently mine, we are not going to get anywhere near that. So from a geopolitical point of view, crude oil is it. We are seeing things like lithium becoming issues in terms of geopolitics and who controls the supply chains for, pardon me, lithium or graphite or nickel sulfides, but they fade in comparison to the weight that the oil and gas industry has in modern world economics and by default geopolitics. Now, those of you that are students of history will know that during the Second World War, the American government then went and split up the oil cartels. Effectively, oil was cartelized in America because of the massive control in the value chain that the oil companies had. They effectively were operating as nation states within a nation state, and they were controlling the market prices in terms of supply and demand. But as we're moving towards our energy transition, and again, this is not the first time the world has done an energy transition. We've had small energy transitions in the past, but they all have been hydrocarbon based. So if you go back into the late 19th, early 20th century, there's a large dependency on coal and whale oil for heating and lighting. As soon as crude oil and the petroleum products became well known and a lot cheaper, we had the move from coal to an oil and gas based industry. And now, obviously, with the concept of global warming, we're moving away from a hydrocarbon based driven society into what we're hoping is going to be a more carbon neutral, energy efficient society based on metals and minerals. Now, nation states and NGOs tend to divide these, as I mentioned earlier, into two different groupings, what's referred to as critical raw materials, which are economically driven, and strategic raw materials, which is mainly an American concept, but is now getting traction within the EU and the United Kingdom because those have defense purposes. They're very closely linked, but in specific cases, there are very unique metals which have to be sourced for military purposes, but they tend not necessarily to be mined in bulk. They tend to be either co-products or byproducts. So, for example, if you're looking at selenium, which is critical for modern military technology, it tends to be mined as a byproduct out of VMS base metal deposits. So if we're not mining our VMS deposits, we're not getting our selenium. Again, it tends to be economically driven. And what we also are seeing in terms of the overall global market, and again, for those of you following the news, you would have noticed, for example, the Ghanaian government is pumping millions of dollars into lithium projects in Ghana. British government has released, I think it was £250,000 to a company called Cornish Lithium to help them with lithium brine extraction. They've spent another £280,000 supporting a junior exploration company looking for nickel sulfides up in Scotland. So we're now seeing governments directly investing in metals and minerals project. Now, what's this going to have in terms of economics and reporting of economic viability in terms of the CRISCO reporting standards? That's something which is still debated. We were debating it at the CRISCO AGM last week, especially also with what's referred to as the Critical Raw Materials Act, which is legislation passed in the EU, where the EU will grant you money if you report your project, if it's of a strategic nature. It has to be reported in terms of the United Nations reporting standard, UNRMS. They don't mention any of the CRISCO reporting codes and standards, which we are all used to as geological professionals. Now, a lot of times people automatically default to, well, critical is the global north. So your G7 type countries, and everybody's worried, or most literature that you read and most press statements read are America's worried about this or America's worried about that. America's not the only country that's concerned. This is an example of India's current critical raw materials list. And you can see is pretty standard compared to the American one or the EU one or the one that you'll see from Sweden or Canada or Australia. They're all very readily available, and they're very accessible on the internet. If you want copies of them, drop me an email. I'll gladly send you those documents. Some of these metals, though, if you start looking at them, there's generally a lot of, well, why? Now, if you look at antimony, for example, South Africa's got some of the largest antimony deposits in the world. They just tend not to be economically viable or extractable under our current economic environment. So the amount of money it's going to extract versus the amount of money to process, it makes no sense. Again, this is why you're seeing the move of nation states into funding these type of projects. So for those of you that are sort of sitting here and have had experience of the sort of the Russian system, there is a certain degree of a command type economy coming through. How far that's going to develop, that's probably something is very early on to see and to understand the dynamics of that. But we are seeing countries do, as I mentioned, direct investment to secure these metals and minerals. So another subsidy provided by the taxpayer. What I also want to cast you to start looking at when you know, as I'm talking about this, is certain things here are almost like a why. Rare earths we all know about, is talked to death. Something like silicon. Now, so most people say, well, you know, silicon is just sand. Well, interestingly enough, silicon is not just sand. Yes, there's a massive demand for sand for construction, and as the world population grows and we need infrastructure, especially for going carbon neutral, we're going to need massive volumes of sand and cement and water, which is an entirely different discussion about criticality, is we're going to have to mine and develop those. But silicon is critical both for our modern infrastructure. So computer chips are silicon based. If you're doing fracking, you need a specific type of fracking sand, again, very unique. And if you're having fiber optic cables, again, you need high quality silicon. It doesn't exist everywhere in the world. And then things which are, you know, most people don't consider really sexy minerals like tin. Tin, again, you know, most people think tin cans, solder. Again, tin is making a comeback. We need it for a lot of our critical technologies. Maybe not in a huge amounts, but they are critical for the modern technologies that we need. So India is also concerned about where they get this stuff from. So you can see that as much as India is a large country, it has a lot of metals and materials. It is also very, very dependent on the importation of these critical raw materials from other countries. So have a quick look at the right-hand side and see who are the countries that India is dependent on. Now, the first thing that's going to jump out is China. Now, for those of you that are aware of the history of India and China, they have fought several border wars. So even though they are partners in BRICS and they share common borders and India is importing from China, there is underlying geopolitical issues there. So if China decides to cut off supplies of lithium, then they have to go to Russia. Russia and China, for example, have good relationships. So maybe China cuts it off. And then where do they go to? Well, India will then need to find either lithium deposits in country, or it will need to start talking to other countries to try and get lithium imported for the technology. Another disruptor which may or may not impact us as we're going forward is the expansion of BRICS. So again, for those of you that are not aware, BRICS has now admitted a number of new nation states into it, so including countries like Argentina, Saudi Arabia, Egypt, UAE, and Iran. This will change in many ways the geopolitical landscape. So again, if you start looking at the G7 nations, so the 7 richest nations on Earth, you look at the landmass area, the resources that they've got, this is something which has the potential to radically change the way the world operates. But it also gets us back to metals. Now, if you start looking at this, copper, critical to what we're doing, major copper refining is in China. But also, why Iran? Why is Iran going to change things? Obviously, with the geopolitical tensions in the Middle East at the moment. But also one of the things that most people forget is Iran has massive undeveloped copper deposits. Before the revolution in 1979, companies like Rio Tinto and BHP were exploring heavily in Iran for large copper deposits. For those of you been following the news with Barrick Gold, Reko Diq is the current asset that Barrick is developing, massive copper deposit, but you can see it is on the same tectonic belt, so the same areas for exploration. Lithium processing, we have the same thing. Now, I need to caution you on 2 points. When lithium reserves are talked about in some of these slides, if you go to the Wilson Center, they tend not to be referring to the Crisco type of reserves that we're familiar with. They're talking about the reserves that would be reported in terms of UNFC. So not quite economically viable, but it's the total amount of metal or mineral which is potentially extractable. Other things to just be aware of is not every single lithium project or copper project gets onto some of these infographics. So again, just treat them with a grain of salt. These are in general mainly diagrammatic or descriptive in nature. So when we start zooming into Africa, now if you cast your mind back, Africa had 1 or 2. I just want to draw your attention to all the activities in Zimbabwe. Again, for those of you that are not aware, most of these assets have been sold off to Chinese concerns. And we're talking about billion US dollar type transactions. Up in Ghana, this is the asset that the Ghanaian government has just invested several million US dollars into as well. And if I remember correctly, this is one of the Lion Lithium projects. And again, massive investments from overseas because they're seen as good long-term and high-quality assets. Now, in many ways, as countries and nation states start looking at criticality, there's a number of different methodologies, so I won't go into that. If you want to understand the methodology, go to the hyperlink. This presentation will be made available. But what we're also seeing is even though there's a mathematical process to follow, countries are now overwriting things. So if you look at, this is the EU critical raw materials list, copper and nickel have been manually overwritten to show criticality. Copper, why? Well, we've just seen in terms of, well, China controls the vast majority of copper processing, but also nickel, if we're starting to look at moving to a carbon neutral environment, you need very specific types of nickel. So nickel laterites don't have the quality of nickel that you need for your electrical vehicle. It has to come from a nickel sulfide type deposit. So again, we can't just say, well, we've got nickel, what is a type of nickel? The same when we're looking at things like graphite. What is the type of graphite? Amorphous graphite cannot be used for some of the type of things that you would need a large jumbo flake for. So you can't make graphene or spherical graphite from a amorphous graphite type deposit. You need specific type deposits. You need to understand the potential deleterious elements that are coming in some of these deposits as well, but also what are the potential co and byproducts coming through. So moving forwards, if you're not aware of this, China has cited national security that they are restricting the export of graphite. And again, midstream, China controls 80 to 85% of graphite manufacture, and China has the stranglehold effectively on the manufacturing of spherical graphite and graphene, which are critical, as you can see, in battery anodes. So again, if China gets upset with the way things are going, they have the ability to go and restrict supply chains, which will then have a knock-on effect in terms of costing, because supply and demand, if the demand is up and the supply is down, prices will increase. But let's move away from talking about metals and move on to something slightly different. Most of you are familiar with Maslow's hierarchy of needs, and the critical thing in terms of human needs is food. Okay, so our basic needs, which translates into food. And from food, we translate into fertilizer. And in terms of fertilizer, we look at 3 primary elements: nitrogen, phosphorus, and potassium. And you can see the impact that they have in terms of the growth of vegetation, which is necessary for food. And looking at it, there's a whole load of different ways that this is processed. So I'm not going to get into this. You can, again, go to Fertilizer Europe to go and get some more detail on this. But you can see from here, we've got 2 different geological rock types. So phosphate and potash, neither of these are replaceable. So these are truly diminishing resources and reserves. So once phosphate is gone, it's very difficult to recycle, if not impossible, and the same goes for potash. But we need these critical raw ingredients into making fertilizers, which are critical for crop growth and crop production to feed the world. And you can see that we've seen an overall increase in fertilizer production. This is the most up-to-date slide I could get. Forecast indicators dropped off in about 2023, again, arguably due to a certain degree of price drop and global economic slowing down. That, again, will have an impact on this. Also, there's some geopolitical issues that I'm going to touch on as we go through. But again, this is just to reinforce, since 1950, we've had a massive increase in the world's population. It's referred to as the Great Acceleration. Reasons why, lots of them, but post-Second World War, cities were rebuilt with new sanitation systems. You had rollouts of vaccination programs. You had anti-malaria programs coming out. You had the creation of the then World Health Organization, the United Nations. So overall, human longevity or mortality dropped off. But we also see our population growth being restricted to very unique geographical regions. So you can see India and China specifically, but also to a certain degree, Indonesia are some of the world's largest population areas. Nigeria is going to be one of the most populated countries in Africa, but you can also see Rwanda, Uganda, and Burundi are also got massive population growth. All of these people need food, and to supply that food, well, we use a lot of fertilizer. Now, there's not quite a direct correlation between the use of fertilizer and population density. That's because different soils have different, what's referred to as reactivities. So you don't always need as much fertilizer to make your soil fertile as you do in other areas. I'd like to draw your attention, however, to Brazil, as we're going to discuss Brazil going forward. But when we start looking at the basic concept of fertilizer, you can see there's also geopolitical factors at play. So from this food sensitivity analysis, you can see in not only have China played games in terms of restricting rare earths, restricting graphite, restricting lithium, China has also played geopolitical games in terms of stopping fertilizer exports. When they do that, the price goes up. We've seen it with an impact also with the Russian invasion of Ukraine, and we're going to start looking at some of the other implications of that. In terms of the economics, though, they're pretty massive. So, as I said, let me draw your attention to Brazil. Brazil is a net importer of fertilizer to the tune of 15.2 billion. It is a major concern for the Brazilian government. There's a briefing today to the Brazilian Ministry of Mines in terms of, well, how do they try and get to a degree of autarky, which is effectively self-sufficiency in fertilizer production. A lot of you will be saying, but just wait, Brazil's got the Amazon rainforest, they've got tons of land. Well, the thing is, Brazilian soil is very acidic, and as soon as you slash and burn the areas where the rainforest is, the soil is not nutrient rich, and you maybe have one or two crops, and then your plants don't grow, and then there's another move to slash and burn. So basically, you've cut down the rainforest, you've had maybe 2 to 3 years of crops, and then the soil is exhausted and you need to move on. So again, ongoing replenishment of nutrients into soil. So let's start looking at some of these in a little bit more detail. Now, the first one we're going to look at is nitrates. Now, for those of you that can remember 4 or 5 slides back, it didn't actually talk about rocks at all. Interestingly enough, some of the first fighting over natural resources were due to nitrates. So, but how nitrates form, they tend to be found in the Atacama salt flats. So again, the areas where there's now a lot of exploration for salars, for lithium. But going back historically, there was no other source for nitrogens. And nitrogen is important in fertilizer, but it's also important in explosives. So ammonium nitrate, so ANFO, based on nitrates, the only place to get them at that stage in world history was in the Atacama Desert. The way that it's done is, you can see on the right-hand side, is basically a hard pan. The hard pan is ripped up. You put hot water on it, and the nitrate leaches out. It's as simple as that. Mining is still going on to this day. It's a massive ecological disaster. The problem is, because it's in the middle of nowhere, no one looks at it and no one really cares. It did, as I mentioned, result in a war. So this is a fight between Chile and Bolivia and Peru from 1879 to 1884. It was all about taxation. So again, even going back then, taxation causes people to get upset. At the end of the day, Chile won the war, getting large tracts of land from both Bolivia and Peru, and effectively having a monopoly, or a very strong monopoly, on nitrates. That lasted until about 1913, until this gentleman came on the scene, a gentleman called Fritz Haber. Fritz Haber created the Haber process, which is a synthetic way of taking nitrogen from the air, mixing with natural gas, and creating ammonia. Ammonia you can then use to make fertilizer or explosives. Things were going okay until we have a little bust up called the First World War. This is when the process started accelerating, because obviously Germany gets isolated from the rest of the world due to the First World War. They no longer have access to the Chilean caliche, so they start developing this process. Unfortunately, though, this is not the reason why most people remember Fritz Haber. Fritz Haber is probably more infamously known for this. He was the first person to recommend the use of poison gas during the First World War. He was Jewish, so while he did create this and helped Germany to some initial victories during the First World War, during the Second World War, or in the 1930s, he was exiled from Germany because he was Jewish. But probably more of interest to us as geologists is we're now getting onto the current rock type stuff. So phosphate, this is a phosphate operation in Togo, which I visited. Large operation, government controlled, has a number of unique characteristics to it. It is high in cadmium, so heavy metal, you can't extract it, it goes into the body and it builds up. For those of you who like chocolate, it also builds up in cocoa plants to relatively high levels. So the World Health Organization created new guidelines for levels of cadmium in chocolate. It also has a very high calcite content. So before you can use phosphate coming from Togo, you need to calcine, so heat it up, burn off the calcium carbonate, and then ship it out. So where do we find these things? Well, phosphate's located all over the world. Some of them are in larger, more continuous belts than others. You can see that there's large potential phosphate deposits under the sea. There was in the late 1990s, early 2000s, a lot of projects looking at exploration of phosphatic rock off Namibia and South Africa. None of those developed further because there was a lot of environmental backlash to them. You can see this large belt extending through Africa, going through Algeria, Morocco, Egypt, Jordan. Interesting things in terms of some of these belts is the mineralogical composition changes. So the phosphates that you've got in Senegal going up into Morocco, Western Sahara, they're all pretty high quality, very low contaminants in them. As soon as you start getting over towards Egypt and going through into Jordan, Saudi Arabia, they have a relatively high uranium content, and the World Atomic Agency has looked at these as alternative sources of uranium as part of phosphate mining. So again, when we're starting to look at geopolitical issues, we're not always necessarily looking at a single commodity. They could be other offtakes or alternative metals and minerals coming out of your primary commodity that you're going to be mining and processing. From a geopolitical point of view, though, you can see some countries have more phosphate deposits than others, so it puts them in a position that they can potentially control the market for those products. We also need to understand the different types of deposits we've got. Sorry, I'm running a bit out of time, as normal. We need to understand the different types of deposits that we've got and the economic viability. So, as you can see from here, we can start looking at carbonatites. They tend to be relatively low in contaminants. The problem with them is that they tend not to be as reactive, so you normally need to blend them with something else. And a lot of these the carbonatite deposits tend to be associated with rare earths. We move to the sedimentary deposits. They tend to be larger and more extensive, open pitable again. The problem with sedimentary phosphate deposits is they tend to be associated with potentially with a lot of contaminants. So as I mentioned, cadmium, uranium, arsenic, all tend to tie up, iron, carbonates, all tend to be associated with your sedimentary phosphate deposits. So again, having a large phosphate deposit doesn't necessarily mean you're going to have an economically viable phosphate deposit, because you may not be able to process the phosphate out, or you need to blend your phosphate deposit with material coming from another source, which has, say, for example, low cadmium. Phosphate itself moves through, and you can see that at each stage in the processing cycle, or the cycle that we use phosphate in, there's losses. This ends up leading to contamination and algal plumes coming through. So we need to take it further. Now, there's been a lot of discussion in America, for example, about processing human waste for the phosphate content. Again, it's not anything new. It goes back to this 15th, 16th century where urea and human feces were used for this. The problem tends to be that human feces tends to be contaminated with high levels of currently, well, plastic amongst other things now, but also high levels of heavy metals. So it doesn't always make it conducive to being reused and reprocessed. We also start seeing a significant increase in the use of phosphate in batteries in cars. So again, we're not just seeing the requirement for phosphate for food production, we're also seeing it in our move towards a carbon neutral economy. Phosphates in and of itself has numerous supply routes. I would refer anyone looking at supply chains to this website. It goes through a whole lot of other things. It's not just phosphate and fertilizers. You can look at various metals, minerals, and other commodities coming through. But what is interesting is you can see again how Brazil is a net importer of phosphate into the country, as well as countries like China being a net exporter to countries which they don't always necessarily have good relationships with, like Indonesia. So again, depending on the relationship a nation state has with other countries, you can end up having control or lack of control on your resources. So from a Brazilian point of view, they're dependent on Morocco, they're dependent on Egypt, and they're also dependent to a certain degree on China. Egypt is now joining BRICS. China is part of BRICS, so is Brazil. So theoretically, there should be more stability. But again, local issues between, say, Brazil and China could change that situation very quickly. But closer to home, what we found is Morocco, through the OCP group, which is basically the Moroccan State Phosphate Company. I'm not going to try and butcher the French version. There's two issues. First of all, there's historically long debates and discussions that Morocco have effectively occupied Western Sahara. And the reason why Morocco is occupying Western Sahara is due to high quality phosphate deposits. But in and of that, Morocco itself has got relationships with 12 other African countries, and effectively Morocco or OCP control the flow of phosphatic fertilizer into those countries. So again, from a geopolitical point of view, depending on the relationship that Morocco has with those countries, or say, for example, Nigeria has with Morocco, it could influence food security in that country due to the relationship. A similar thing goes for potash. Now, most of you, when you're doing research on potash, China doesn't even make it there. Interesting enough, China does have significantly large potash resources in the Lop Nor area, where they tested their atomic weapons back in the 60s and 70s and later 80s. But it tends not to be that well known, and it tends not to be that well discussed within the literature. So China in and of itself tries to become self-sufficient where possible with natural resources, but even then China still has to import natural resources. As a side, China's recently got into bust up with Myanmar, because Myanmar provides between 20 to 30% of all the rare earths that China needs for its industry. So again, even China is not totally independent in terms of access to critical raw materials. The same argument can be done with nickel. So when Indonesia stopped exports of nickel to China, China then promptly retaliated and started entering into agreements with the Philippines and New Caledonia for sourcing of nickel, and in many ways Indonesia lost out and have started to have to create new relationships with other countries for the nickel. So again, you can see potash deposits spread over the world. For those that can remember back to the slide for phosphate, you can see potash and phosphate tend to be geographically related. And for those that are in the oil and gas industry, yes, there's also correlation between oil and gas deposits, phosphate deposits, and potash deposits. They're not necessarily all on top of each other, but they tend to be spatially located. So if you've got an oil and gas deposit, there is a chance that you're going to either have a potash or a phosphate deposit near there. And again, we have various types of potash deposits. Each one has their own characteristics. Probably the one that most people are looking at the moment is potash brine deposits, which has been part of discussions with the Crisco Lithium Brines Working Group, which I'm part of. Basically because in Australia, a company called Callium Lakes have just went bust. And again, is trying to understand what they did or didn't do correctly in terms of their resource estimation and declarations. And you can see again by country who controls what. Canada and North America are currently the world dominating potash suppliers. And effectively the Canadian market is cartelized, so is very much a case of the price structure is relatively consistent. That being said, we are going to be seeing an increase in the requirement for potash going forwards, but as you will see for the bottom left-hand diagram, North America, so America and Canada are still going to dominate the potash market as we move forward. The key players that you can see on the top right-hand side, again, dominantly Canadian countries, but I want to draw your attention to JSC Belaruski, which is a company we're going to be having a quick look at. But the potash market in and of itself is dependent on supply and demand and price cyclicity. So what the potash market is now saying is they're now going through what they're referring to as the fourth wave. The BHP report is quite insightful into this. But what BHP and the potash market in general is predicting is we are going to start potentially seeing a price uptick overall due to geopolitical tensions. But again, there's a lot of uncertainties and there's certain things that have happened in the market which may or may not represent that going forwards. Again, we can start seeing where material comes from and goes to. If you look at the Canadian-United States relationship, this would be a classic case of what's referred to as nearshoring or friendshoring. So Canada providing to America and theoretically having very good relationships. Brazil, again, being very dependent on China and Belarus, amongst other places. So again, if there's any issues or uncertainty in terms of geopolitics, so like the Russian invasion of Ukraine, and sanctions against Russia, it means that Brazil, for example, has potential issues with supply. Russian potash tends to be slightly cheaper than Canadian potash. So again, Brazil will have to pay higher prices to secure its food supplies, or at least its fertilizer for its food supplies. So Belaruski mine in Belarus, I think it provides 8% of all the potash requirements in Europe. Interestingly enough, during the Ukrainian invasion, what was not stopped was Russia and Belarus's exports of potash at all. It was Lithuania's unilateral decision to ban the importation of potash from Belarus, which caused the local price spike for that. And as you can see, again, how dependent at least the European market is on the production of ammonia, potash and phosphate coming from Belarus, Russia, and Ukraine. So we're now looking at a local geopolitical issue. So by truncating or cutting those supplies, or at least disrupting those supplies, it has a knock-on effect in terms of fertilizer price, which has then a knock-on effect in terms of food price. And this is the potential issues in terms of food security worldwide. As soon as we start restricting these supplies of these minerals, that people tend not to think about because they are bulk, low value minerals. They are really, really important to feeding the countries that you live in. And that leads me to the conclusion. I guess I should probably explain this before we move on to questions. The turn of the century, there was what was referred to as the matchstick girls strike. Matches at that stage was made from white phosphorus. Current matches are made from red phosphorus. White phosphorus causes a disease known as phossy jaw, where the phosphate destroys your jaw bones. And that's why it was one of the first known unionization efforts by a group of very low paid workers in terms of health and safety. And effectively what they did with this is to get white phosphate matches referred to as Lucifer's band. The only people that tend to use white phosphate now are military in white phosphorus schinates. So anyway, any questions? I'm more than happy to try and answer them.
Safisa, we have a hand. Go ahead.
Hi, Mark. Thanks for the talk. Do any minerals straddle both the CRM and SRM boundary, i.e., the critical on both the defense side as well as the non-replaceable side, if I can put it like that?
It's just the way you tend to define them. So the Americans tend to look at it from a military point of view. The rest of the world tends to look at it from an economic point of view. So things like copper, nickel, cobalt, vanadium are referred to as strategic raw materials by the Americans, and the rest of the world refer them to critical raw materials. So it's really who's talking about it. What America does and what America has done since post-World War I is have national stockpiles. So what they will then do is they will have a national, so like South Africa has a national stockpile of oil. So if oil gets cut off, then South Africa theoretically can operate for, I think should be able to operate for 3 months to 6 months with the strategic stockpile. America does the same thing with metals. So the Department of Defense in America operates these massive stockpiles of the metals and minerals, which are considered critical to the well-being of America. What has happened over time is periodically the Department of Defense and Congress and Senate will look at global risk and will decide, do they need to get additional selenium or gallium, or do they feel that the risk profile has dropped off, and then they will sell out whatever metals and minerals they think are no longer critical and they can replace easily. And that has some interesting consequences. I think back in the 1970s, America decided that, I think it was aluminium was no longer a critical or a strategic metal, and they went and effectively dumped a whole lot of aluminium on the market and created an artificial price decrease, which caused some interesting issues. And the only way that the aluminium market recovered is by moving beer companies, interestingly enough, moved away from using glass bottles and tin cans to using aluminium tins because it was a lot cheaper and they saved a lot of money and made more money. So, so that there's some interesting causes and effects which can happen when you're starting to, upload or download large amounts of metals onto the market.
Right, we have another hand. Go ahead.
Hi, Mark. Thank you very much for the talk. It's actually been very enlightening. I think for me, I think the biggest thing that stuck out was the absence of Africa in the whole discussion on CRMs and SRMs. And I think maybe we are disillusioned as Africans, I'll speak for myself, that Africa is resource rich. So is it correct to say we are resource rich, but on the global scale, it's minuscule what we do have? And secondly, what is South Africa doing in the CRM and identifying the CRMs and SRMs? Because I do know that we had a beneficiation strategy at some point. Where are we in that space?
Okay, well, the first thing is I thought everybody was probably bored to death with Africa and CRM, so I tried to do it a little bit more globally. Africa is the focus for most countries to try and source critical raw materials. So China has the Belt and Roadway Initiative. China was investing billions of US dollars in Africa. they've got a local slowdown in the economy. So China's not investing the same amounts of money it did in Africa. And what it is being more forceful about is if it lends money to an African economy, if those loans aren't paid back, they will want resources in kind. So for those, and it's not just metals and minerals, for those of you not aware, effectively China controls the logging industry of Cameroon. China effectively controls the fishing rights of Namibia. China controls most of the offshore potential for resources around Africa because they've been ceded by various African governments. Russia has a presence in Africa, specifically North Africa, through the Wagner military group. So they're providing effectively security to various African governments who may or may not be as democratic as what they could be. So, for example, there's a large Russian presence in Mali and a large Russian presence in Central African Republic. The Second Congo War, for example, again, that was over critical raw materials. Again, people wanting that. So the Second Congo War is rated as one of the bloodiest conflicts in the world. Again, it was all over supply and demand of critical raw materials. Europe's got what they're calling, I think it's the European Friendship Alliance, where Europe is now talking to various African governments to try and secure, it's referred to as friendshoring, to try and have that. The British government, for example, recently signed an agreement with Nigeria for British government will, I can't remember how many millions of pounds the British government will provide, but also technology in exchange for the supply of raw materials. So there's a lot of that type of stuff going on. In terms of South Africa, that is the only BRICS country that I could not find anything on. I couldn't find a critical raw materials list. I could not find any strategy documents. Most other BRICS countries, including China, you can actually find something on the government websites. South Africa, I don't know. South Africa, I mean, apart from PGEs, dominant, manganese dominant, and also there's sufficient potential for copper in terms of, and this is potentially answering another question, Bali's question. South Africa has Phoscor, which manufactures phosphate that used to be blended with the material coming out from Togo. There's potential in South Africa for rare earth deposits. Just trying to get Steenputs, Steenkamp massive rare earth project. So South Africa and Africa have got massive potential for these. It's just, as I said, I didn't think anyone was going to be interested in hearing what Africa has to offer the rest of the world again. Hopefully that's answered it.
Yes, thank you.
Gerrit, I'm not too sure about Mozambique. Yes, Phoscor is a minnow in terms of oil production, but it's still a player because it's got high quality phosphoric acid. There is discussions of Phoscor listing. Whether that happens, I'm not quite sure. So Tanya will be happy if they do list it. The discussion I've heard is going to be on the JSE. So in Bali, yes, South Africa can produce phosphoric acid, and it is produced primarily out of Palabora. There are a number of smaller carbonatite deposits. Glencore, for example, was mined in the 80s and 90s by Goldfields for phosphate. And I believe there's a company now, Glenover, is now looking at it for potential to produce rare earths, but there doesn't seem to be very much movement on that project for the last 10, 15 years.
Right. So Kathleen has over 27 years experience in the mining industry, primarily in African mining projects. She's a director and principal consultant at Redbush Geoservices, a geological consulting firm where she's been working since April 2016. She's previously worked at Coffee and Goldfields. She provides geological services to clients that include geological interpretations, modeling and estimation of resources, design and monitoring of quality control systems, assistance with mineral exploration and beneficiation test work programs, and review and advisory services. Kathleen has worked as a competent or qualified person for reporting in most jurisdictions, including SAMREC, JORC, NI 43-101, US SEC, and others. She's assembled a team of associates where necessary to assist clients with a full spectrum of review and advisory services across geology, all engineering studies, public reporting, and preparation of regulatory reports. She's also a technical trainer through Deca Dynamics, where she's developed and delivered a series of courses on mineral resource estimation, public reporting, geological, and other topics for online and on-site public courses in Africa and Australia, or private courses tailored to the needs of corporate clients, including AngloGold Ashanti, Metarex, AusIMM. Thank you very much, Kathleen.
Okay, thanks for that introduction. And right, so we're going to talk about examples of exploration triggers and reasonable prospects for economic extraction. And I'll give you, these are going to be examples from the phosphate market. Okay, and I know Mark is no longer online, but Mark has actually just given a fantastic introduction. There are a lot of things that I cut out of my talk that Mark has put in. So moving on from Mark's discussion on just global sort of, I want to say, on from some of the more global aspects of the minerals industry and strategic minerals. My talk is going to look specifically at the phosphate market, and from the time of its inception in the 1800s. So phosphate is actually a relatively new mineral in the mining industry. So we've actually got pretty good records, and we can show you some of what's happened over a period of time and why certain companies dominate the market and so on, and what some of the options are. So it is a critical raw material, as Mark said. We literally cannot live without it, and it's necessary for all food production at this point. So disclaimer at the beginning, this presentation is my personal opinion as of today's date and time, okay? The information on companies named in this report does not represent the official opinion of any companies, but they're my opinions about these companies. The author's opinions are based on my experience to date, the format of this presentation, limited information that it may entail. And most of the information I'm going to present is from publicly available sources, with the exception of the historical information on the Cabinda phosphates. And just a warning, my opinions are likely to change when presented with new information. Okay. The other one is an acknowledgement to Minbos for permission to use the COFAN and Energo data, and they have reviewed the content related to their deposit. However, the opinions expressed are still remain mine and not theirs. Okay, just a quick picture on showing the phosphate cycle. Mark actually showed a complex flow diagram, but this basically shows you where the phosphate cycle. The ultimate source of all of the phosphates is generally alkaline volcanic rocks, although phosphates is found in a lot of other different rocks, which is one of the reasons we use it as a so-called major oxide in our XRF analyses. It's present in most soils and is a limiting factor on plant growth. It's absolutely essential for all cellular life on Earth. It flows through the system primarily through agriculture. All right, and there are some industrial uses outside of the agriculture, but it's less than 10%. Okay, distribution of the phosphates. Mark's given you one. This is a slightly simpler version. The main phosphate areas there's greens and blues, if you can see the greens and blues. So greens are sedimentary deposits. The blues are various types of igneous, and then we have what we call island deposits, which are some guanos. Right, but most of, so the two different types, primarily sediment is the main source of all of our mined phosphates. So they're called marine deposits. Igneous is maybe 5 to 10%. They have some metamorphic deposits. There are some biogenic deposits, and then there are what they call these residuals that are a result of weathering. In fact, one of the markers that I often use at the bottom of saprolites is to look at the phosphate analyses, because at the bottom of the weathering zone, you tend to get a concentration of phosphorus. Okay, so there's two different maps. The one with the green and blue, that's from the IFDC, and I'll explain who they are later. And the other smaller map is a more recent one from some researchers in China who looks like they completely scoured the world database for any type of phosphate deposit. So it gives you an idea. Phosphate is widely distributed. It's just not necessarily economically distributed. You saw this with Mark. The industry is actually very highly concentrated. Okay, there are basically 5 main players. They control most of the phosphate distribution in the world. That's OCP Morocco, Huizhou, and the Yunnan phosphates mines in China. Mosaic, which is an American company, it has mines in the US and Brazil, and Apatite in Russia. Okay. The map on the side, this is also phosphate reserves. You'll notice Australia supposedly has a lot of reserves. They don't seem to be able to get them to market, and I'll kind of explain why later. There's South Africa. Those who are asking about South Africa, South Africa has very good phosphate reserves, and we're going to talk about that later in the presentation. And they're actually considered a major phosphate producer, even though they don't even come close to China, the US, and Brazil. Okay. Okay, the next bit, the phosphate consumers. And again, following from Mark's talk, the distribution of phosphate resources or reserves versus the users are not, it's not always, from a geopolitical point of view, it's not always a nice balance. Now, China has large reserves and they are the largest user. India is the second largest user and it has effectively no phosphate reserves. Okay, it has some deposits, but they're not very good. The United States is the third largest user, and it still has very good phosphate reserves and resources. Brazil is the fourth largest user, and it has a genuinely huge mine producing phosphate. It doesn't produce anywhere near enough for the local consumption. And these 4 countries consume 62% of the world's currently commercial phosphates. The next 9 consume 17%, and these are literally the next biggest consumers. And in bold, I've put the countries that consume over 1 million tons. There's 1, 2, 3, 4, 5, 6 of them, all right? And they're the next highest producers. So you can see where there's a bit of an imbalance here. South Africa, I put, just for interest, I put where this is our consumption. It's not our production. That's our consumption. Okay, so Russia is interesting, even though it's a huge producer of phosphates, or it has been historically a huge producer of phosphates, it currently does not consume very much. And there are good reasons for that. The next one, and I think Lenert was asking about Africa. Yeah, Africa. Africa, this is the fertilizer consumption for Africa, this lower map. And I want to just put a pointer in here. So this map shows the fertilizer consumption from 1960, and it's getting somewhere. And you'll see most of the increase is actually in nitrate consumption. There's an increase in phosphate, which is the middle one, up until about 1980. Then it kind of doesn't do much, and then there's actually a decrease in phosphate consumption in Africa from 90 up until the mid 90s. And this is problematic for a whole lot of reasons. There is a slight increase in consumption, but again, generally just nitrates, nitrogen, up until about 2010. And this is one of the triggers. We start seeing additional consumption of phosphate in Africa. Okay, so we want to talk about what triggers the exploration and exploitation of these natural resources, and as I said, the phosphate demand. So the big one is changes in population, all right, or market demand. So how much of it's needed, changes in lifestyle, again, how much is needed, and what product form, and movement, where is it needed, because where it needed changes over history. Changes in technology is a very big part of what the phosphate industry. Okay, so what the product is used, how do we get it out? How do we make it into a useful product? And how do we get it to the end consumer? The changes in capital, which is both money and taxation. Taxation apparently plays a huge role in all of this, as Mark even alluded to. So how do we pay for this? Changes in political structures. And this is the political structures affects the phosphate market actually quite heavily through its history. And the last one, especially for fertilizer, is changes in local climate changes, either local or worldwide variations. And in fact, the impetus for having phosphate as a fertilizer is in fact climate change in the 1800s. What part of the impetus, shall I say? Okay, so the first trigger we have for exploration and exploitation of the phosphates as a fertilizer is in 1830, England needs more food, and it has a fast-growing population. There's a development of the United States. It's a new country. There's expansion into what they call the Midwest. It's just a huge, enormous tracts of farming land. And a lot of cheap transport by water. So shipping becomes a really viable and cheap way of moving large quantities of material. And also the NPK was understood to be the macronutrients for plant nutrition and supplementation. So short history, pre-1800, we don't actually know much about phosphate use. There are indications that the Romans may have known about the element phosphorus, but it's a bit vague. And phosphorus-containing materials are obviously used in fertilizers for centuries, for millennia. Mostly in the form of animal wastes and burning of vegetation. Well, it's primarily a potassium. There is a certain amount of phosphorus in that, in the ash. In the 17th and 18th century, bones are the major source of phosphorus and fertilizer itself. And the active components were not understood. So they were putting it on the ground, but they didn't actually know what was causing it to actually work. The first recorded isolation of elemental phosphorus by a hobby alchemist called Henning Brons. You can Google it, and it's a really hilarious story. He definitely wasn't looking for phosphorus. He was looking for something that would turn lead into gold. But its use was limited to, I politely use the term medicinal cures, but that's actually quack cures and party tricks, because when phosphorus is exposed to oxygen, it glows green. So it glows in the dark really nicely, and it goes bang. Right. So basically for about 130 years, nothing really happens. Phosphorus is identified in bones by the end of the 18th century. But again, not much is done with it. However, the first phosphorus matches, they do isolate phosphorus, and they're starting to make matches. Again, Mark alluded right at the end about the Phossi jaw. Again, you can Google it and read about the history of the matchmaking industry. It's with the phosphorus. It's actually a really terrible story. And they realize that this is not a good idea. So they do use phosphorus in modern matches, but they use it on the striking pad and not in the tip of the match itself. 1840. Now this is actually a major change pretty much in science generally. So a guy named Justus von Liebig, he's considered the father of organic chemistry, and he does a whole lot of really, really interesting experiments. And one of which is he confirms that the fertilizing effect of humus on plant growth was due to the inorganic salts of potassium and phosphorus and nitrogen. Potassium doesn't seem to be working in here, but they do eventually realize that the potassium is part of the equation. And so it's not the organic carbon-based matter that's actually causing the nutrient effect. So he tries treating bones with sulfuric acid to extract the phosphate for fertilizer, and it doesn't work. So he kind of gives up a little bit on that one. About the same time, a man named John Bennett Laws, who owns a property called Rothamsted, it sets up an experimental station. He's experimenting with all sorts of agriculture. But he also starts experimenting with treating bones with sulfuric acid to extract the phosphate for fertilizer. And his fertilizer is actually effective. So this is the first sort of phosphate fertilizer, chemical fertilizer on record. Right, so how did we get to there? The agricultural advances in Europe generally is leading to a certain amount of population growth. So we have we get a Chinese plow in the mid-1600s, which is much faster, and it literally decreases the horsepower. So you don't need to use as many horses. It gets your crops, tills better, and so they can get better yields. Mid to late 1700s, the Industrial Revolution starts. We're moving people, as you can see from the graph, people in England and other places start moving into the cities as urban. Mechanization and farming starts in the late 1800s. And then what happens in England is from about 1800, the population just starts growing exponentially, and it outstrips the agricultural production. So the population growth is about twice the increase in agricultural production. By 1830, England can no longer feed its population. And this is a really big problem because, you've got to go buy food. Fortunately, England has got money to buy food, but they still have to solve their agricultural yield problem. This is partly where the Rothamsted experimental station comes in. And they're looking at fertilizer to increase the yields. Okay. This is the first trigger. They literally need food. Okay, so John Bennett Laws figures out that his method of making fertilizer works. The problem is his bones are in short supply and they're very expensive. So he eventually, somewhere, and I don't know how they figured it out, somewhere in East Anglia, they found these coprolite beds. So it's basically fossilized feces in a shale. They're able to mine it, and he produces this first superphosphate in England. His company that he founds in 1947 lasts actually until 1968. So it produced fertilizer for 120 years. At the same time, we have guano coming in. And when Mark's talking about the critical minerals list, with the US they've had lists for years. 1856, they passed the Guano Island Act to make sure they could secure enough fertilizer for the agricultural production of the United States. Potash starts becoming mined in Germany. And then the first commercially successful phosphate mine actually opens up in South Carolina in the United States to produce phosphate rock for chemical fertilizers. And then the major jump is the discovery of the phosphate rock in Florida. Now, the phosphate rocks in Florida is a monster deposit. Again, it's been producing now for 142 years, and it's still going pretty strong. The next run, again, is in the United States, where they find phosphate in Idaho. Now, they're looking for gold, but anyway, like everything else, they didn't find a whole lot of gold, but they did find the Idaho phosphate fields, and the mining starts. The next jump comes where phosphate mining, they find phosphates in Tunisia. It starts a little bit early as small-scale mining, but proper commercial mining starts right at the end of the 19th century. Okay, and these are all feeding farms, obviously the United States and Europe, almost primarily. The second trigger for development of the phosphates, synthetic ammonia, all right, the Haber-Bosch process, it actually starts in about 1910. Okay, so this has two effects. Obviously makes nitrogen a lot more readily available, but we also, the guano yields are also dropping a bit, but with the invention of the Haber-Bosch process, they don't need to import as much guano for nitrogen. And not bringing importing the guano also decreases the amount of potassium and phosphate, because the guanos are complete fertilizers, so they have NP and K to some extent. So we're still looking for more. Agriculture is increasing. 1920, OCP in Morocco is founded, and this is the largest known deposit of phosphate in the world. And it's either Florida or Yunnan in China, which are the second biggest ones. So one of the things on this graph, if you look, we steadily have, this is phosphate production. They're steadily increasing. So we bring it in with Morocco. None of these are going crazy with massive amounts of production. They're producing enough that the world needs all the way through. However, something happens in Mexico in 1940. So the US has a research station, Tennessee Valley Authority. Many of you who know history know about this, but they had an agricultural research arm, and they were looking at improved grain production. And they introduced improved maize varieties into Mexico to increase the cereal production. The problem with these grains is they need a lot more fertilizer than the more traditional or the less improved and the non-modified varieties. So the TVA is also involved in producing concentrated fertilizers, including phosphate. So up until about 1940, most of the phosphate is what they call single superphosphate. It's not highly concentrated. We start getting things like triple superphosphate, and you also have, with the synthetic ammonia, you have the nitrogen phosphorus fertilizer combinations. Okay, but really the big kick comes right about 1940 with these improved high yield maize grains. They eventually follow with maize in Malawi, but I don't have good information about it. Okay, so this is happening during World War II. 1945, World War II ends, the whole globalization starts to begin. And then there's a major push for agricultural development across the world. So really 1945, right at the end of World War II, world populations are starting to actually increase if you look all the way through. And also the advent of these concentrated fertilizers, including the phosphate, allow easier use of these phosphates. It's cheaper to transport triple concentrated phosphate than single concentrated phosphate. And the fertilizer production just really starts to take off. And this is across the board with the potash. It just goes up and up and up very quickly. Okay, so the next one. Okay, so we have high concentration fertilizers in the 1950s, which is the third trigger for production. So we get more out. The other trigger, and this is the major one here, 1960s, you have improved the same TVA that was involved in Mexico is involved in improving rice strains in the Philippines and India in the 1960s. So they've got really high yield grains. Separately, China develops its own a bit later. However, rice requires enormous amounts of fertilizer, especially phosphates. So a lot of these increases in production is due to rice, improved rice grains. Okay. All right, so we need the production. The other thing that's actually happening at the same time, again, after World War II, a lot of the colonial governments and other ones, India and the US, are also looking for mapping of strategic materials. Now, the US has been involved in this for a very, very long time, and they continuously map their strategic minerals. But other, especially colonial governments, started doing a lot of mapping, especially in Africa. You see a lot of geological survey data from the 1950s and the 60s. So major efforts in mapping natural resources, and there are many new phosphate deposits are discovered, especially in Africa and South America, because they're not as well explored. But yeah, 1950s, some of them do something. So Senegal and Togo, They've identified the phosphate deposits and they start to look at doing something with them. But in the 60s and 70s, there's exploration and evaluation of some of these phosphate deposits, and a few new mines come on stream. So Senegal, Togo definitely come on stream. Palabora comes on stream. But many of these exploration projects fail. Okay, there are a lot of reasons for them failing. The mid-1970s, there's a price spike with generally high commodity prices, but no major projects come on stream. And the only reason I can think of that is there's plenty of supply coming from the United States and Morocco and Russia and China. China's also already on stream by the 1970s. So I did need to put in China and to just explain China because it's part of the next trigger. What happens in China? The Ming Dynasty collapses after a famine in 1644. China then develops fast maturing rice. So they've got double cropping. They're already needing quite a lot of fertilizer for their land, but they don't have a lot of land under production. So it's not too serious a problem yet. From 1650, they make a lot of agricultural improvements, the Qing Dynasty. And the main one that they do, that the Qing Dynasty gets set up, is the supply chain management of the food. So for nearly 200 years, they don't have any major famines. However, by the late 1700s or the early 1800s, China's got the same problem as England. Their population has doubled, but they cannot increase their yields anymore. For various reasons, the colonialists, First Opium War, so the wars with England specifically, start. That doesn't help the problem, and the Taiping Rebellion eventually happens in the mid-1800s, destroys the food management system in China. So we're not having a lot of fertilizer use here because the agricultural system is just not functioning properly anymore. After the Taiping Rebellion, the Qing Dynasty does make a lot of improvements in agriculture and farming methods. So something similar to what's happened in Europe in the 15 and 1600s. But they never get to a point where they've got a lot of fertilizer production. After the PRC is founded, they look at all of this. Food is a big issue. There's a massive increase in agricultural land that's brought into production, irrigation, machinery, mechanization in 1980. This up in 1957. And then obviously with improved rice yields, more agricultural land, they need fertilizer. So the Yunnan phosphates deposits now start being mined in China. And they're still the primary supplier in China. In 1973, you have high yield rice strains, and they are very, very, very hungry rice grains. So they use, currently it's about, I think rice uses about 4 times more phosphate than wheat and maize. And of course, China's population explodes, India's population explodes, Africa's population explodes. Western Europe, not so much. And the United States keeps, they just keep going. You just go to the next one. Right, the fourth trigger that we have, and this one I'm going to discuss some of the projects. The fourth trigger is in 2006, is a lot of it's traced back to the US housing crisis. Okay, there's a few things. In early 2010, the United States increases its maize production by 50%, primarily for fuel production. Okay, so they don't eat the stuff, they put it in their cars. The US housing crisis causes a rise in commodity prices, and there's a transfer of investment capital. So you see the price spike. There's a lot of speculation involved here. It's not just fertilizer that goes up. A lot of commodities, except for gold, just spike. There's also, we regularly get this peak phosphate scares every once in a while. So there's a lot of peak phosphate noise in the media, how we're going to run out of it. The other trigger is in 2010, a lot of places become a little bit easier to access. There's some political change in Africa generally that makes it a lot safer to just work in certain places that we couldn't get into, say, 15 or 20 years ago. There are export restrictions from China are put on, and and this happens at peak, what they call peak DAP, which is the blue line. So the export restrictions on China happens here, and it's only then that the phosphate rock sort of starts to rise. Okay, and from 2010, we get an increase in phosphate and potash exploration. So there's this massive gap between sort of 1980 and 2010 where not actually much is happening. All right, so I just want to show you, these are deposits in the mines and the failures and the successes. So the general rule here, the really big projects pre-1970 generally succeeded. Okay, in the 1800s, the United States really need fertilizer. Europe desperately needs fertilizer for growing populations. And there's enough money to get them going. They also have the large production they want. They have good economies of scale. And the early starters, at least in Florida and Morocco, are pretty successful. Idaho is is another story. There's a lot of ways of how not to do government mineral policy in Idaho, which prevents a lot of mines from being developed there. Yeah, but small projects. So the big projects pretty much succeed everywhere. What about some of the small projects? East Anglia is the first commercial phosphate mine, believe it or not. It's a small production, but the main reason for this is proximity to the Rothamsted Research Institute, and it's also nearby the Southeast England farms, so they have a market. It's tiny. The production is probably a few thousand tons at most. South Carolina, again, we have phosphates are discovered. It's a reasonably moderate production. I think it just closed recently. Again, proximity to a major agricultural area. Tampa, Florida, these are the monster deposits of the Gulf. That's 142 years and they're still mining. And this is proximity to major agricultural areas. And you have cheap transport. So Florida is supplying the American Midwest, and they can get fertilizer and materials up the Mississippi River, all the way up to Ohio, and I think Minnesota at the time. So they can literally supply the whole central part of the United States. They're right on the ocean. They can supply Europe. They can supply Brazil. They can supply pretty much whoever they can get to. So it's almost like, and they also have, eventually after the 1940s, they have potash from Saskatchewan and they have gas from the Gulf, so they can pretty much make as much fertilizer as you want. Tunisia and Algeria, late 1800s, it's a very high quality product. It's like the Tunisian phosphates are almost as good as commercial triple superphosphate in efficacy. So these are really highly desirable. And again, it's right near major markets in Europe. You can put it on a ship to Marseille or to Rouen or wherever, or Antwerp, and get it cheaply. The funny outlier here is Peru, and Peru, Namibia, and then the Pacific. Now, these are guano deposits. They're very high concentration. They're NPKs of varying qualities, but they're very high quality product. They're very low cost to mine because you're literally scraping it off the surface. And again, all of these are right near coast. You can put it on a ship and you have really cheap transport. So Peru, and you also have the nitrates from Chile is the same part of the same system. So yeah, Europe is getting guano from Namibia in the 1800s as well. So for these, the combination is generally proximity and cheap transport are the main triggers, and that's what keeps them going. Pre-1960, a couple of things change. Now, Idaho is a bit of a strange one. So when I had a look at Idaho, Idaho gets developed as a strategic resource for the government, and there's a whole long history, and it gets really complicated. and it's very badly managed until fairly recently, actually. So it's discovered in 1889. There's some production gets going in 1908, but it's not until after the Great Depression that it really gets going, mostly because of bad government policy. Palabora is discovered in 1904. We know this, but it doesn't start producing phosphate until 1953. So again, it's a proximity, and there's obviously a change in government policy, especially towards government agricultural policy. Morocco, again, it's discovered in 1908. The OCP is actually established in 1920. We don't have very good information on what happens before that. But again, Morocco, its proximity to major markets. You can put it on a ship and send it anywhere. And they have, of course, the scale of production is just massive. So they can produce a lot of product at a reasonable price. Kibni or Kibna complex in Russia, also discovered in 1923, goes into production straight away. The new USSR obviously needs to feed an awful lot of people, and they need fertilizer. So again, proximity to a major market is Russia and Central Europe. Government policy changes with the USSR coming in. They can do huge production at scale, and the capital cost in the early USSR is less of an issue than actually getting product out. Tapira in Brazil. Now, Tapira, Brazil it produces phosphate amongst other things. It's discovered in 1955 as part of those colonial mapping systems. Production comes very soon afterwards. There are quite a few. It's part of a cluster of deposits. Again, it's got a local agricultural market, a local large area. It can do production at scale. It's a genuinely huge deposit. And the current owner is actually an American company, which is Mosaic. Now, Tapira and Palabora and Kibna also have something in common, is these are co-products. So they produce a lot of other products. So Tapira's got your REEs and stuff. Kibna produces pyrophyllite and a few other minerals. Palabora, as we know, produces copper, magnetite, whatever, vermiculite. A lot of it. It's a multi-commodity operation. Okay. And then the post-1960s. Taiba in Senegal, which is a very large sedimentary deposit. It's got good transport. It's just a little bit north of Dakar, which is a major West African port. It has very low capex, OPEX and capex. Togo, same thing. Togo has, as Mark said, it's got some problems with the cadmium, but it's a very large deposit. Again, good transport. It's near the coast, and the operating costs are not, or have not traditionally been that high. China, what's the trigger for China? Well, Yunnan, the Yunnan, and Hebei is up north near Beijing. Yunnan is down in the southeast. Proximity, obviously, to a large agricultural area, changes in government policy again. And in China, there's a lot of land reform that brings agricultural production in, land into agricultural production. And that seems to sort of stop there. So there's one other deposit discovered in the 1950s. And this is the African story in most cases for small deposits or smaller. So we have Togo and Taiba and Palabora and Morocco, and that's about it. Minjingu is a small deposit in Tanzania. It's discovered in the 1950s. It goes into production in the 1980s. The whole project fails by 1990 and just sits around doing nothing for about 10 years. And then about 2000, it goes back into production. Now, Minjingu, I'm going to give more detail on. It's proximity to local agricultural markets, same thing. It's very, very high grade. It's a very high quality product. And it has a small local market with high value agricultural products. Everything pretty much now stops in Africa, and then not a lot developed in the US, except for some small and medium-sized deposits for local consumption. Okay, just to give a little idea on factors limiting the development. Now, this is from 1985, but I don't think it's changed dramatically. There was a breakdown of amongst other things, of the costs of both operating and bringing on stream various types of deposits. So you see the West African ones. The West African ones are, that's Togo and Senegal, very, very low cost operations. Okay, most of the cost, partly because the transport is really, transport to the port is almost nothing, because literally Taiba is a few tens of kilometers north of the biggest port in West Africa. Christmas Island in Nauru, these are your guano deposits. So Christmas Island is sort of northwest of Australia. Nauru is in the Pacific, and Nauru is also an example of how not to manage your mineral resources. So Christmas Island is still producing. Nauru may have some small production, but it's largely mined out. Also very cheap because they're island deposits. Transport is a higher portion because they have to be put on a ship and they're far away, but it's not a project killer. The southeastern United States, that's primarily Florida, North Carolina, and South Carolina also very cheap production. So it's mostly the mining costs and the milling costs, but Florida, especially Florida, that doesn't have a lot of taxes, still doesn't have a lot of taxes. Transportation cost is very, very cheap because they're right at the Tampa port and you can put it on a ship to anywhere. And the initial investment costs. So the top one is really interesting. And this is largely what prevents new deposits from being open, is this top one, that 15% rate of return on all investments over the life of the property. So all of the first three, West Africa, Nauru, and southeastern US, have very low capital, effectively use your capital costs. Morocco and the Western Sahara have higher capital costs, and they have higher taxes. So these are royalties. The government obviously takes their share. And I don't know how they don't seem to distinguish between royalties to the government and profit to the shareholders. So there's a few questions there, but they're still relatively inexpensive operations. Then we go to Idaho. A lot of these are underground mines. Okay, so they're expensive. Egypt, Israel, and Jordan. Some of these are also underground mines, which is why they're expensive. And Idaho is far away from everything. Expensive transport. Iraq, Syria, Turkey, again, it's right in the middle of a continent. It's all landlocked, expensive transport, and obviously high government takes. And this is South America, which is mostly timber. It is a horrendously expensive operation. Most of it is operating the mill. Now, a couple of things. West Africa, southeastern United States, Morocco, even the western US, Idaho, are sedimentary deposits. Egypt, Syria, and Jordan are also sedimentary deposits. South America are carbonatites. Okay, so the carbonatite is what drives the cost because they're just really expensive. These were other mines in 1985, and they look at what is preventing them from being developed. And a lot of the issues are the capital. It's the cost of capital is killing you. And yeah, it's your cost of capital. Okay, but at that point. Okay. This is looking, so people, Lenert, you asked about Africa. So what about Africa? So these are the mines that were not developed in the pre-1960, and there's a few reasons why they weren't developed. So there's Panda Hills. Now, in all the phosphate literature, Panda Hills, there's Panda Hills, there's Panda Hills. When we looked closely at Panda Hills, it's a small deposit. It's a carbonatite. So it's a combination. It's now trying to be flogged as a rare earth project. There's another one nearby called Nguala. It's also one of these combination phosphate rare earth carbonatites. They're very small. They're co-products. You have to mine everything together. The production costs are very high. The infrastructure is not very good there. So there's a rail line, but there's not enough electricity, there's not enough gas, there's all kinds of issues. And because they're carbonatites, they're acid only, and that it becomes an important. You cannot use the material from a carbonatite directly on your fields. It has to be processed to phosphoric acid, and it has to be made into a chemical fertilizer. Okay, Tlemcen in Mali, there was some, that's like this literally in the middle of the Sahara on the Niger River. There has been production locally, but its current political instability just completely prevents any development. Other West African, so we have, you see Taiba, you can see where Taiba is, and the Togo, and there's lots of little deposits all around them. A lot of these are just geologically difficult. They're isolated, there's no infrastructure. And the production costs are just plain too high for the local market. Western Cape, we've had a few bits. Now, Western Cape, I'm talking about onshore Western Cape, not offshore Western Cape. Onshore Western Cape, there are some small sedimentary deposits that have sporadically produced phosphates. There are currently 2 on track for local production. We'll see what happens with those. Okay, I know of at least one where you could potentially use it as a direct application phosphate rock rather than having to turn it into a chemical fertilizer. The West Coast here, these were discovered in the 1950s. A lot of them are just plain uneconomic. They're technical problems. You couldn't actually get in, and there is some sporadic local extraction. The West Coast offshore. These are really, really interesting. And aside from all the environmental objections, they're just not technically feasible at this point. But these are potentially enormous, huge, like Moroccan-sized, huge deposits. Okay. Also, from an economic point of view, they'd be too expensive. You're not going to compete with Morocco on price. Okay, right. So Minjingu, my one, this is a really interesting little deposit. And I do mean little, it's quite a small deposit. So Tanzania, it's discovered in 1956. Tanzania gets its independence in 1961. Like a lot of the countries who were independent, there were other priorities than getting a fertilizer factory up and running. But by the late 1980, they are attempting to produce local fertilizers. They set up a company to produce local fertilizers. But what happens in the late 1980s is that there just isn't enough fertilizer on the market. And a lot of aid, fertilizer as aid, agricultural aid is dumped on the market. And the more expensive local producers just can't compete with free fertilizer. Okay, so a lot of things just really, they collapse across the board. And if you remember earlier in this map where the fertilizer production really starts declining in the late 1980s or usage, you get decline, and you get a decline in agriculture. Now, a whole lot of things go wrong with agricultural policy. Some of it has to do with the aid, probably good intentions leading to bad outcomes. So Tanzania was in fact producing phosphoric acid. Someone asked about phosphoric acid production. They're producing phosphoric acid from this Minjingu phosphate, but that again closes in 1991 for a whole lot of reasons: management, mismanagement, lack of a market to pay the high costs of production. And then generally there's a decline in agricultural production into the mid-90s. Okay, so it looks like it's not going to do too well, but changes in government policy again privatizes this MIPCO. It changes its name to Minjingu Mines and Fertilizers. So they do have a resource, and in fact a reserve sitting there waiting for someone to do something with it. So they don't need any exploration, but they do need to figure out how to produce the fertilizer here. So, and like I said, small, it's a 10 million ton-ish, 20% P2O5. possibly a little bit more, but it's never going to be a massive, huge deposit. However, this project has it's a relatively low capital project. It has small production. So it's only the maximum capacity right now is about 100,000 tons of fertilizer annually. It has a very low OPEX and it has very efficient engineering. So what they've done here is instead of just buying an off-the-shelf fertilizer plant, they have redesigned something to be cost-effective and easy to run. It produces complete fertilizer, NPKs, and the other thing it does is it produces a very high-spec organic fertilizer for the specialty marker. Okay. So that's actually where we're going to go with that one. The next one is Cabinda. I'm running very low, so let's just, I'm way over. Phosphates are discovered in the 1930s during petroleum exploration. A second evaluation in the 50s, regional mapping, and it discovers some inland deposits, not just the ones on the coast. So this is Cabinda. You've got the exploration. For COFAN 68 to 73, it fails, and it fails for a few reasons. The management can't agree on what product they want to, they go local or they go export grade. There's insufficient tonnage and grades for a major mining house, so they try to sell it to Anglo. And it's just a really badly run project, and the work is terrible. It's just, everything just goes wrong here. Angolan civil war from 75 to 2020, plus trouble in Cabinda, basically makes Cabinda off limits until about 2010. However, in the meantime, the Yugoslavians come in. It looks like an aid project of some sort. They evaluate one of the big deposits, but nothing seems to happen there. We saw 2007-9, there's that rise in commodity prices and a perceived underinvestment in new resources. Spurs phosphate and potash exploration in the West Coast. So it's Congo, Angola, and Gabon. The Minbos Kikata is recognized for the first time as having potential. So everyone's concentrating on these deposits because they're big. So they want their world class. They want to try to compete with Morocco, which just doesn't work. But this little Kikata down here, which everybody ignored, now starts looking really, really interesting. More exploration work. Now, again, there's a failure of this project. Why? Same thing, RPEEE, yes, it looks good, but the tonnages are not attractive for long-term contracts with fertilizer manufacturers. Same problem that the COFAN guys had. We have the fertilizer price, the phosphate rock price drops by about 60%, and then it stays very low for a while. Then they start looking at it another time, but again, there's problems within the management and there's a joint venture. That joint venture fails and the exploration permits are terminated. So largely same problems as COFAN, management issues, can't agree on a market, and the tonnages aren't good enough. 2020, the project revives. So the Minbos guys get the Kakata phosphate concession in a tender. There's a new scoping study, and they completely changed the focus of the production to the production of fertilizer rather than export of phosphate rock. They also have some advantages. The port of Cabinda is being developed. They have cheap electricity now and economic free zones. They've done their agronomic studies, so they show really good results for a direct application fertilizer rather than building a phosphoric acid plant. Definitive feasibility studies completed in 2022. And what they've done, again, possible value added products. So if you look at Mark's, some of the later comments, we have its products for explosives, we have green ammonia, we have yellow phosphorus, we have for batteries. And so they've got batteries, commercial farms, they're going to supply explosive to the mines, they're going to supply normal fertilizers. And the project development starts. So yeah, sorry about that one. Okay, so factors that change the projects from failures into successes were change of government policies and more stable political environments, better infrastructure, local development, local transport networks, general market improvement, agronomic testing. So they check to, they're producing targeted fertilizers, and the change of a focus from high cost, low value add exports to more local, high value add end consumer products. Okay. I'm going to just skip the last one. Okay, then the last two more slides. Last trigger. So there's been a spike in prices recently, obviously because of wars, mostly in the Ukraine, but now in the Middle East. And is this I spelled it wrong, is this a trigger for the next round of exploration and development, or is it a temporary blip? So this is what's going on. I think Mark has shown you the reasons for the blip: COVID, government policies halting exports, or tariffs, loss of international exports from Russia, Indian subsidies. The Indian government subsidizes fertilizer, so it increases use, declining production in the US, and China. The other one is China has had a declining phosphate use for quite a few years now. So that's one that we don't always take into account. So I don't know where it's going, but we have lots and lots of phosphate. The USGS estimates that with the especially those South African offshores, that we have enough for 1,200 years at the current rate of consumption. Okay, there's still organic sources for local small scale and market gardens. So we're not going to run out of extractable phosphate anytime soon. However, localization or sources from friendly states is likely to be a driving factor in the foreseeable future. And this is where the real panic starts, and the critical and strategic component comes in is, do the people who have them, are they our friends, and will they sell it to us? There's also a need for local sources of fertilizer producers at small scale to cater for local markets, especially in the tropics, because the big fertilizer guys do not make specialized fertilizer for tropical climates. TSP, just as soon as the monsoon comes, that fertilizer that you put on just washes away in the rain. And there's also scope for niche and organic markets. Right. And if you want some more recent interesting information, these are some references.
Good morning. I'm going to talk about the importance of the reasonable prospects of eventual economic extraction when declaring a mineral resource. And obviously we call that RPEE. So that's going to be what I'm going to be looking at today. The point of departure is not to try and go through all the estimation parameters and all that. It assumes that we've known geology, we've got a geological model, we've got a block model, we're probably in the process of classification, and we are trying to look at that important aspect, reasonable prospects of eventual economic extraction. Now, the important part of this one is that we need to consider the factors that are significant to both the technical feasibility and the potential economic viability before we do the declaration of the mineral resource. And that can be quite a complex situation or quite difficult to do. And there probably be a number of opinions about it. I'm going to present some of the aspects that I think are important and hopefully give you some idea of a way to go from here. So RPEE, and just to highlight what's going to come next, is the E for eventual is going to fall away. So we're in a situation where eventual is covered by the word prospects, so we're not going to be looking at that intently. So RPEE, we see that in the code we need to do some sort of assessment, and within the code we have definitions for scoping study, pre-feasibility study, and feasibility study. However, really we don't have to consider the assessment a scoping study. It can be, but I wouldn't recommend it. It takes a lot more effort than is generally acceptable by our clients or our commissioning agents. Definitely not a pre-feasibility study and definitely not a feasibility study. Those would both be applicable when we're doing a mineral reserve determination. So a scoping study might be in there with a chance, but the Canadians would call that a PEA. So that would be considered something that would be useful to do. I think in many cases it's a little bit more than is actually required. So when we're looking at it, we need to assess the threats and opportunities that are associated with the mineral resource estimate. And those are generally in a whole lot of disciplines that we are not considering only in the geological aspect, and we're going to go through quite a few of those as we proceed today. The things that we need to look at. We need to look at both technical and economic parameters. We need to look at the modifying factors. So although the modifying factors are related to reserve declarations or determinations, we need to look at them. So almost in inverted commas, look at all the aspects of the modifying factors and include them in our assessment. One of the aspects that's, so then it would be all of those, mining, metallurgy, environmental, social, and obviously economic. So look at all of those, and now I'm going to go through some detail in that just to give you some of my ideas in that respect. Fatal flaws. So what I often look for are fatal flaws. Let me give you an example. Quite a while back, I was asked to look at a deposit that was in the Sahara Desert. And the commentary that I got is that we can go there. It's about 100 kilometers off one of the major roads. And I'm pretty sure that major road was not a tarred road. And so it was in the middle of nowhere. So in terms of fatal flaws, one would have to say infrastructure, real issue here. And when we talk infrastructure, we'd be talking personnel, power, water, all of those things. So would that have been something that would be reasonable to consider? Well, possibly not. The client didn't go any further with that, but that doesn't mean that it was something that shouldn't have been considered. What I tend to do is do some simple modeling, simple economic modeling, looking at some of the costs, some of the revenue parameters, and then possibly comparing to adjacent mines, adjacent shafts. Now, one of the aspects here that is probably nice to, or one should consider, is in mineral reserve determination, when they do a sensitivity, probably the most important aspect that comes out, or the most sensitive, is revenue. And revenue is not only the commodity price, it would also be the grade and the recovery and quite a few others. So that's the most important, most sensitive one when doing an assessment. The other one that's next on the line is strangely enough operating cost, and rather than capital. So capital is important, but invariably operating cost is something that one has to consider quite well. And using adjacent shafts, other mines, particularly in the same jurisdiction, when we're needing to import, and there will be considerations of what governments would be prepared to give in terms of concessions, etc. So those would be broadly some of the things to consider. Restrictions, I call that a binary approach. There's certain things that if that is there, you would say no chance, we can't go there. For instance, a national park or a wetland or a community. Those would be considerations you say, it doesn't matter what the economics say, it simply can't happen. So all of those need to be considered, but let's go through some of them a little bit more. So RPEEE, reasonable prospects for eventual economic extraction. We, and the recent CRISCO meeting, that the eventual has been taken out, so reasonable prospects for economic extraction. And it's made a lot of sense. So that's going to be proposed, or it is proposed, for all the codes going forward. Let's look and see what Table 1 of SAMREC says. So Table 1, there's one section, 4.3, about the reasonable prospects for eventual economic extraction. Obviously, I can't change these aspects now because they're they're going to fall within the next run of the code. So we need to disclose and discuss the geological parameters. And these will include, obviously, but not limited to volume, tonnage, grade, value, or quality estimates, cutoff grade, strip ratios, upper and lower screen sizes. That would be to do with diamonds. And there are a few others that we'll discuss a bit later. We need to disclose and discuss engineering parameters. These would include the mining method, dilution, processing, geotechnical, geohydraulic, and metallurgical parameters. As I say, I'm going to go through these a bit more individually. Disclose and discuss infrastructural aspects, including but not limited to power, water, site access. Disclose and discuss legal, governmental, permitting, statutory requirements. Disclose the environmental and social or community parameters. Disclose and discuss marketing parameters. And what sometimes is the one that is almost exclusively considered. Disclose and discuss economic parameters or factors which include but not limited to commodity prices and capital and operating costs. Obviously discuss material risks, and we currently got in the code we need to discuss about eventual, but the word prospects tends to cover that, so I don't think that's necessarily something we have to worry about. And if we're being reasonable, we won't have an eventual in 100 years. We'll be much more realistic about that. So let's move on to discussing the RPW aspects individually. So remember, firstly, that whatever you declare, you will need to be prepared to face your peers. So whatever you do, someone might well question you. You need to be able to justify what you're doing in such a way, or what you've done in such a way, that they would be happy to consider what you've done as reasonable. What one would consider is what other people would consider reasonable, and if something you think is a little bit beyond that, then I think that you would want to justify it in some way. A reasonable, this is an opinion that I found, it's an opinion or judgment that could be held or made by a reasonable person with experience in the industry. So when we talk about peers, we would be talking about people who are within the industry and are doing similar sort of work. So we need to be able to face them and consider that as reasonable. So let's go through the various technical aspects. Geology, obviously having a geological model, having an own structure. If there's an aspect of the structure that can be an issue, and that this runs on to aspects of geotechnical, so hanging wall for underground, side walls and high walls for open cast, those would be important to understand. Obviously things like dilution, so the low grade material that might come out. So in this particular picture, although the grade is highlighted by red, the other material would have to come out, and would that make it profitable? So that would go towards things like minimum width. So all of these aspects should be considered, and probably when you've got to the stage of making that determination based on your profession, you would probably be a long way down that road. The other aspect there that I haven't highlighted, which will should be considered geometallurgy, what the minerals are that are there within the deposit, and where there are different sulfides and oxide minerals, one would want to know what they are so we can go ahead with those. Geotechnical, as I said, they're going to be, the geotech guys are going to want to know about the geology, about structures, about lithological contacts. And the picture on the top right, if you have a joint set or bedding that is not favorable for a high wall, need to make sure that it's there and consider that that might well be a fatal flaw. And if it isn't, there might need to be a way to deal with it. And obviously when you deal with it, it comes with cost. Strip ratio would then come along with that. If you have a very flat-lying deposit, your strip ratio tends to be higher. So you need to understand that depth would be associated with that. All of those sort of things, they'll feed into later. Now, as we go through, you might think that I'm considering everything from almost from a feasibility aspect. No. going through some of these things, just making sure that you understand that it's not something that is an issue that you can reasonably say we can deal with it. That's great. So things like underground pillar designs, you don't need to do pillar design. Making sure that that when you've thought about it, you've considered it. One of the estimates that I did a while ago, there was a shear zone in the hanging wall. So the pillar design had to change. Now, was it a fatal flaw or not? Should we have considered it? Did it add cost? Yes, it almost certainly added cost and changed some of the design parameters. But having that in the consideration was important. Another aspect is sterilization of mining units. Where you've got multiple units, you might be in a situation where some units are sterilized because of the geotechnical aspects. For underground mines, where the middling between different units, depending upon the competency of the rocks, might well affect how we've done it. So those are things that should be considered or need to be understood. Mining methods, we're not expecting, I don't think, to have a full-on idea of the mining method. Simply underground or open cast, and maybe cave mining or block cave mining for kimberlites, etc. All that would probably be reasonable. If you're in a situation where there's going to need to be some sophisticated version like a board and pillar on an apparent dip, might need to just check with the mining engineer what those would be and if that would be an issue. Pillars, I've discussed losses, mining losses, what would be there and what would be the reasonable extraction ratio. Dilution, what material would go outside which needs to be taken out, and obviously that would also be related to things like hanging wall and footwall aspects. Capacity constraints, I wouldn't worry about that most of the time, but there might well be hoisting or tailings limitations, and that might well be something you need to consider. So be aware of those. And once again, remember I said that sometimes these things are binary. If there's an issue, then you have to rethink things from the beginning and might be not disclosing other aspects. Geometallurgy, I touched on briefly. So understanding the mineralogy of what is going to be extracted. Now I put up there some of the copper minerals. Now each one of those is different. They're copper, they're oxides, hydroxides, and sulfides. And if you've got a number of them, you might well not be in a position to have a single metallurgical flow sheet. So that might well be something you say that we can't do it. And for instance, if you have native copper in a deposit, that could change things quite dramatically. I think invariably you're going to need to understand sulfide oxide and whether that reduces the recovery, and that would then possibly circumvent some aspects along that way. But just having an understanding of that would be, I think, important. Recovery, clearly, the better the recovery, the more likely it's profitable. Where we have refractory minerals, understanding that and being sure that you've actually covered those. Multiple metals, that can be an advantage where you've got a number of metals like rare earths or PGEs, where there are a number of metals that can contribute. That's fantastic. Deleterious elements, being sure that there isn't something that would preclude mining and rather recovery. So that would be something to be important. And then there's also a list of aspects that could influence recovery quite dramatically. Lithology, alteration, mineralization type, metallurgy, mineralogy, grain size, the texture, oxides or not, density, hardness, all of those can have an effect. And having some sort of very basic idea of what's there, I think is important, but I wouldn't necessarily go into too much detail. Once again, consider them, and generally they're fairly obvious, so it shouldn't be too much of an issue. Infrastructure, so roads, rail, ports, water, power, those are important depending upon the commodity. If you're looking at something like coal or iron ore or bauxite, things like ports become important, rail becomes important, having an idea what those are. And then the other one is surface restrictions. If you're having an open cast, and there's a village or some other aspect that would be a restriction, you need to know about it, and you might have to limit your declaration as a result. Tailings, I mentioned capacity. An aspect there would be also aligned or unlined. Obviously, that changes the cost dramatically, and it might well be something that becomes a showstopper in the end. Effect on the water table, that needs to be, I don't think you need to be concerned about it, but that would go along with lined or unlined, whether you've got arsenides or sulfides or whatever in the material, and that could be an issue. A suitable site, yes, that would be important to have, and that would go along with capacity as well. Environmental aspects, they are obviously becoming more important. This can be quite tricky from a resource declaration aspect because there may be very little known because no environmental studies have been done, but invariably you would have some sort of idea of things like national parks or wetlands or the like. So it's unlikely that complete permitting has happened, and you might not know really what the impacts are or what the zone of influence of a potential operation is. But those should be in some way understood before you progress too far. Social, well, that can be a showstopper. The graphic on the right-hand side is the situation of Rio Tinto when they took out a Aboriginal site, and they were lambasted as a result. But knowing whether they're there or not, that's also important because that would be a potentially showstopper. Things like the culture, the customs, the cultural heritage, obviously those are important. Where resettlement is required, that should be considered, and that might once again be a showstopper from both from a community perspective and from a cost perspective. However, some things like social infrastructure and services, those can be an advantage to a community, so those could be brought in. Employment is another one that would be something that's positive and not negative. Social license to operate, we want to avoid that. So if there is a very militant situation, one should talk to our commissioning agent or client and find out what the situation is. And probably all aspects of this are can be discussed in some detail. And when one does the declaration, probably put some of these things down, partly to remind yourself that you've done them, and partly to ensure that there's nothing that you've missed or assumption you made that might well need to be updated at a later stage. There are obviously other aspects that you might want to consider that are not ones that I've mentioned. Political influence, policy certainty or uncertainty can be big issues. Construction capabilities or timelines, those are things that would be considered. Permitting issues, not only environmental, straight mining permits, water, etc. So those things might well be things that need to be considered. Is it reasonable for a mine to actually get those? Prospects, so remember RPEE, that's the P for prospects. The possibility, which is obviously not proven, of meeting with a success in the future. So all these technical things, aspects that I've been discussing, they both have a prospect of whether it's going to work or not, and they've got financial associated with that. So there will be some uncertainty, and looking at that and considering what uncertainties are there. Then we move on to economics. So RP, the first E, economic. Commodity pricing is important, and predicting what that's going to be in the future is really important. As we know, that can be quite a challenge. Things that go along with that are things like offtake agreements, net smelter royalties, etc. A common way to alleviate that is to find consensus pricing. We know that that's really just herd mentality, but it does give you some defense when going forward. Capital costs are important, and the associated operating costs, and obviously the two are related depending on whether it's an owner-operated or a contract-operated mine. And things that shouldn't be forgotten, things like closure costs. Those could be big issues, and things like lining and unlined tailings dams, as I've mentioned. things like royalties and taxes and whether there are holidays for that, incentives that governments might have provided. So all of those can be brought in, but doing a very simple model with revenue and revenue based on commodity price recovery and point of reference. So it might be a situation where a mine is producing a concentrate and selling a concentrate rather than selling a pure metal. So all of those should be considered in some way or other in a model. So the revenue stream, and then costs, and then things like capital costs and how long it's going to be put out into the future and paid back through profit from the business. Very simple spreadsheets work really well, and then it's really good that you can then do a sensitivity analysis and determine what cut-off prices would be realistic and what would not. An aspect of this is markets and what the future markets are. A few years ago, lithium wouldn't have been on our radar, but now it is. So that's a new market that's developed, and there'll probably be quite a few. The other markets have changed over time. Uranium wasn't a market for a long time, has become a new market over time. Palladium, a while, 10 years or 15 years ago, it really was not considered to be the darling of the PGMs, but because of the change in autocatalysts, became more important. So those things can have a serious effect on your reasonable prospects. Difficult to predict, but important to realize that can be the situation. The commodity uses, obviously things like the new markets would consider lithium and graphite, etc., because those are new uses, and some old uses like coal might slowly but surely disappear. So just understanding what that is from a reasonable prospect, and although we don't have eventual in the code anymore, it's important to understand that could have an effect. So going back to where we started, significant factors that are significant to the technical feasibility and potential economic viability. I don't think you need to do a full feasibility study, but you do need to do some assessment. You need to look at what's reasonable, both from a technical and economic perspective, and looking at significant technical aspects that could affect an operation, good and bad. Viability, obviously important, and you can't just because you've done a block model assume that it's got reasonable prospects of economic extraction. You need to go through this exercise in some way or other. So let's close with a few aspects that are there. So RPEE is a requirement and has been for a long time, is underlying fundamental concept for the declaration of a mineral resource. The factors that are significant, both technically and economic, should be considered, or must be considered, in fact. Considerations for RPEE include demonstration of the technical and economic potential of a conceptual operation using reasonably derived parameters. So going through some of these aspects that I've discussed with you, I think those are very important. The assumptions have to be reasonable, must be clearly defined, and should reflect the level of information, knowledge, and stage of development of the mineral property at the time. So things like economic and environmental and social might not be well understood, but one needs to consider them as best as we can. So I'm trusting that what I've discussed with you has meant something, has been able to give you some perspective.
Right. So we welcome Moses Ndazi. Moses is a specialist in mineral exploration, resource evaluation, and estimation, and project management with more than 18 years of experience in the minerals and mining industry. He has extensive experience in exploration and resource evaluation.
Sorry,
and has held
they're trying to help us go, but nobody could read the Portuguese.
Oh, sorry. Okay, let me carry on there. Tanya's busy. He has held the position of a senior and project geologist with several mining companies in a number of African countries, as well as Australia, for commodities such as coal, iron, gold, diamonds, uranium, phosphate, PGM, and base metals. Moses has been directly responsible for the discovery and development of a number of mineral deposits in Tanzania, vanadium deposits, bushveld minerals, to name a few. There's a very long list here, Moses. Moses is a fellow of the Geological Society of South Africa, holder of an MBA from Wits, and a part-time PhD candidate at the University of Johannesburg. So Moses, with that, if you would continue, thank you very much.
Thanks, Nicole. I'm very sorry you might have heard a lot of noise in the background. I'm also here with my colleagues from the company Luso Global Mining. I want to thank you and Lolly and the organizing team for having accepted that I should bring in my team of geologists to come and witness such presentations, such events. As Nicola said, I'm the exploration manager for Luso Global Mining in Cameroon. I'm leading this base metal project in Cameroon on the Tem complex in the south of Cameroon. Just a brief outline of what I'll be talking about. It's gonna be the introduction, basically just an overview of Cameroon. And I'll tell you why I just tried to give a bit of overview of Cameroon and then the geology of Cameroon as well as a sort of regional geology before we zoom down to the Tem complex, which is the topic of discussion. I'll talk a little bit about the previous work that has been done, exploration work, obviously, on the Tem complex by some guys, Asembe and Co, and then get to Ngomezap, which I said is a case study, but actually is the project on which we are working. Like I said, it's a project for base metals, copper, nickel, with an eye on gold and some critical raw materials as well. We've touched a bit on critical raw materials. So overview of Cameroon, I'm not sure if the headings and subheadings actually show on your side there, but it looks like the enlargement of my slides, I did too much and then cuts off the headings. But yeah, Cameroon, with the capital, political capital is Yaoundé, and the economic capital is Douala. You could relate that to Pretoria and Johannesburg in South Africa. It's a member of the Economic Committee of Central African States. Before then was a member of ECOWAS until 1983, before the 6 Central African states, including Central Africa, Chad, Equatorial Guinea, Gabon, came together to form the ECAS. And Cameroon is a part of that. Politically, it's been stable for quite a long time until recently. We had a few issues with Boko Haram in the north and some unrest in the northwest and southwest of Cameroon, which is more of a protest against suppression than actual conflict. Cameroon is the 10th highest GDP. It has the 10th highest GDP in sub-Saharan Africa. In Africa as a whole, it's about the 15th. So the economic conditions in Cameroon is a bit favorable for foreign investments. The corporate tax is about 3.5. VAT, no, sorry. Corporate tax is about 38.5 and VAT is 19. That's a little bit higher than what we have in South Africa. I was going to say the GDPs projected by the African Development Bank to grow up to about 4.2 from 3.5 in 2022. So the fiscus is conducive, as I said, for foreign investment. And the reason why I gave a little bit of highlight of this was because Cameroon in the past has been dependent on oil for a very long time. And following the past fall in oil prices, the government of Cameroon started looking at hard minerals as another option to boost the economy. And for that reason, the modified the mining code a bit and gave exemptions for exploration companies for the first 2 years of operations, just to encourage foreign investment into the country. All right, like I said, a brief geology of Cameroon as the original geology. The geology of Cameroon could easily be divided into about 4 or 5 eras or sections, if you want. Beginning in the south with the Precambrian, Archean rocks, which are mainly the northern portion of the Congo Craton. And particularly, I was trying to put up this as a general geology to explain why the Ntem complex, which is this area here, is of interest, because if we look at even the mining title map of Cameroon, I couldn't get hold of the most recent one. My last one that I have is about 10 years old, and I thought maybe some of the companies that are in there are already out of business, and it was not worth putting it on. But then the Ntem complex is Archean, and then in the central portion there, we've got the central portion of which is mainly part of the Pan-African orogeny, mainly nectar sediments, schist, arenaceous. And then we have sedimentary rocks, mainly in the southwest area, and the littoral as well, and some of them occur mostly up there also in Garwa and maybe in the Lake Chad area as well. But then there is also the fourth assemblage that we could consider, which is the Cameroon volcanic line, starting from Fernando Po, Principe in the Atlantic Ocean, and then going through Mount Cameroon in the southwest and the highlands of the west, right up to somewhere around Gaoundéré, where it turns strike or direction slightly, almost 90, taking maybe a 90-degree turn. Before I zoom on to Ntem complex, which is the topic of discussion, I just want to highlight some of the minerals that are considered slightly or mostly untapped in Cameroon. Includes bauxite, cobalt, gold, copper, nickel, rutile. And as I said, petroleum has been Cameroon's major export for many, many decades. And there is a shift now in that regard to try and explore more of hard minerals. So zooming locally to the Ntem complex, it's mainly divided into 3 subunits: the Young complex, the Ntem itself proper, and there's another one far east, which is cut off from this image, is known as the Anya unit. The Ntem complex is mainly basically made up of intrusive rocks, mainly tonalites, granodiorites, chalcogenic, granitic, cyanitic, and autopyroxenes associations. We also have some relics of greenstone belt that can be found in the Luludorf Ngomezap area, which Ngomezap is the area where we are currently working, actually somewhere around there, and then Luludorf is there. But similar kind of greenstone relics of greenstone belts in those areas. I wonder if this is showing. I think it's showing. Is there a way we can reduce the size of this? I'm very sure that the portion nickel of my slides, because it is in this presentation mode, is being cut off at the top there. But what this slide is showing is some previous work that was done by some guys, Assembly and others. And what they did in 2020 was to use Landsat 8 images and some aeromagnetic images, including in geological and mineral indices maps as well, to determine what the lineaments, including fractures, fault zones, and other contacts, and to determine areas of mineral occurrences, predictive hydrothermal porphyry centers, as they call them particularly. So if we see down the 2 images on our right, the Landsat images that they used, and from that they determined in reddish colors up there and maybe down south here and in the east, occurrences of gneisses and the schists that are more darker red, right, almost occurring together anyway with the gneisses. And tonalites, the dark blue colors, pale blue, and the greenish ones correspond to tonalites, and granites are a little bit more pinkish and reddish. So it was a color composite image association. Furthermore, we also used some aeromagnetic maps to determine zones of lineaments. And as we can see clearly from these two images, there is a clear difference between this southern zone area here and the northern area where there is that represents a low magnetic background, while there is a discontinuity from the area of Metep coming down to, I think, Kut, right down here, all this south area here are areas of high horizontal gradient magnitude values. So, but unfortunately for us in Gomezap, the results that they got, I think they more focus into the eastern portion of the areas of the Ntem complex, and in Gomezap where we are working, that work didn't, I mean, I think there was, the resolution, first of all, there is very, very low, but I think also they didn't produce any map of that area. So we are now currently doing further work on Gomezap, and I'll show you the results of that shortly. Now, from those maps, the aeromagnetic and the Landsat maps, they produce lineaments. The Landsat lineaments had mostly a northeast, southwest trends, west, northwest, east, southeast, and northwest, southeast trends, whereas the aeromagnetic lineaments were more of a southwest, northeast. But generally, almost, if we take globally, it was generally a northeast, southwest trending strike slip occurrence of most of the lineaments, right? What that tells us now is that while the northern area is more or less fractured, the southern area, there are more fractures in the southern areas, which particularly, obviously, fall within the Ntem complex that we are interested in. So there was a lot of tectonic activities in the Ntem complex, which resulted in these fractures and dislocations in this area. But even within there also, there are areas of less dense fractures, and there are areas of very, very highly dense fractures as well. But particularly what we need to note is that that differentiation between the Ntem complex and what is in the north, which corresponds to the Yaoundé group, which is more of a metasediments, as I said, the Yaoundé group corresponds to the Central African Fold Belt, while the area down south is the Ntem complex, and it's on the northern portion of the Congo Craton. And this area of the Congo Craton is one of the least, I would say probably, arguably, the least explored portion of the Congo Craton. So there is a lot of work that needs to be done in this area, a lot of opportunities for exploration work to be done. And as I said, if one looks at the mining title map of Cameroon, most of the companies that are doing exploration in Cameroon so far are actually located within this southern and southeastern portion of the Congo, of the Ntem complex. Because of this, particularly this tradition of hydrothermal porphyries and all deposits that have been determined. In the center of Cameroon, there are far less exploration going on. Mbalam is also somewhere in the south of this area. Mbalam is one of the biggest projects in Cameroon that is being developed. It's an iron project that is being developed at the moment. It was initially started by Sundown Resources, which is an Australian company. They developed it up to one stage, but then changed hands, and it is in the hands of new owners now and new investors. But yeah, just to say, this area here is very interesting, and there are many companies interested in looking at all of these structures that were defined by Asembe in the 2020. So to further prove that, what the guys did, Asembe and the others, was to also use the Center for Exploration Targeting analytical tool to determine what they call the porphyry centers, using data from the magnetic image that they had. From there, they determined that there were about 66 porphyry centers, which correspond to magnetic bodies, that's magnetic rocks, in this area of the Intem complex. Most of that, about 92%, 61 of them, falling particularly within the Intem complex, right? Whereas a few of them were occurring in the Yaoundé group, which is in the Central African Fold Belt. So that means that more of these porphyry centers are found in the Intem complex than it is in the Yaoundé group. And as I said before, even within the Intem complex, there are areas of high high popularity in terms of these porphyry centers. They are more populated in mostly the southern and southeast portion. And as you go towards the north, towards the boundary between the Yaoundé and the Intem complex area, it becomes even less populated and more dispersed and more scattered. Similar kind of thing that we are having, as we're going to see shortly. So what next? So it is on the basis of this promising geology that the company Wori Resources and Luso Global Mining acquired 3 exploration licenses on the Intem complex, Permit 1, Ngomeza Permit 1, Permit 2, and Permit 3. And that together constitute the Ngomeza base metal project, which we, as I said, we are looking for things like copper, nickel, but also the critical elements, lithium, and so on, with an eye also on gold. So after acquiring that, LGM came in and we said that we should do some soil sampling over the 3 permits and see what the geochem gives. So we planned to collect 12,000 soil samples. So far, we've collected 10,000, and then there are about 8,000 samples in the laboratories in Edenville and Johannesburg with ALS that are being analyzed. We've so far got results of about 4,000 samples, I think, yeah, about 4,000 samples results for that, and I'll just show you what those results look like. Results in terms of copper, you can see there, we having very low but consistently occurring little packages, just as we saw on the aeromagnetic maps and the analysis of Asembe and al., pockets of occurrences of indices of copper, but also this is also occurring within a particular zone of interest, this area here, this diagonal north, west, southeast diagonal zone of mineralization, besides some other pockets that go a little bit beyond the zone. But so, particularly 2 things to note, those pockets of indices of mineralization, and then that zone of mineralization that occurs there with a northwest southeast trend. Similar kind of pattern with other minerals. Vanadium is there. You can see that zone there and those pockets that are occurring as well. Those porphyry centers, they actually, I'm also just referring to them as porphyry centers, as Asembe has noted. Similar kind of trend, even with lead, and similar kind of trend with chrome. Our worry is the values are so low that we do not know whether to, and we'll come to that. I'll need some advice on that, whether to continue. Our management is also becoming a little bit discouraged that we're doing too many sampling and all these kind of things, but not the results aren't looking good. But this obviously indicates to us that there is some mineralization. So furthermore, we can see if in nickel, those pockets there, bits of patches there, following similar trend like copper and the other ones. Arsenic, that small point there, but little things all over, scattered all over the places. Same here for silver, small centers, which I think also correspond to porphyry centers, as previous studies have shown. So in conclusion, I think that if we look at the lineaments that is been gotten from the previous studies by Asembe and Al, and the porphyry center maps that they got from the aeromagnetics, including our soils geochem results that we're having, there is a possibility, it is possible that we have some hydrothermal ore deposits within the TEM complex. And I think that is it for me. Thank you. But before I go to questions and answers, like I hinted before, I think we actually need some advice, and even if there is some service that anyone wants to offer, what do we think about these values? They are low, but they indicate the occurrence of minerals. Are we chasing are we just chasing shadows here, or we think that it is something that we should follow up? What we're thinking on our side is to do some aeromagnetic surveys. Geophysics, we are actually tilting towards ground magnetics rather than air surveys, though, but we are welcoming quotations from both sides. If there are people who think that they can help us or give some advice, or maybe even do some work in terms of the geophysics, as I said, yes, my contact, you can send me advice or quotations on that. We are a little bit worried about doing air surveys because of the vegetation. It is in quite dense tropical region with trees that are as tall as 50 meters at times. So the vegetation cover is quite dense. But yeah, we all need some advice and probably some service from anyone who's got something to say. Thank you very much. There's question then, yeah.
Great, thank you so much, Moses. Does anybody have any questions for Moses? Okay, there's one in the chat here, Moses. Is the soil profile deep or shallow? Shallow 1 to 2 meters.
It varies. Sometimes it can go up to 10 meters, right? Quite thick, but averagely 5 meters. There are places where there is no laterite soil cover, but in some areas they are very, very, very thick.